zobaczyć, jak mam tu.
Dobrze.
Mam w
To
komputerze.
tutaj możemy podłączyć się.
Aha, ale nie mam takiego.
A taki?
Taki mam,
No
tak.
to co? To sprawdźmy.
Dobrze. Wszystko jest przygotowane. Aha.
Ten.
Która tam jest.
Aha, dobrze.
Nie, już przełączymy. Nie ma Zbyszka jeszcze nic.
No bo to dwa pointery są chyba, nie? Dobrze.
Dzień dobry.
To jest. To jest online. Online. Się łączy z. It connects with the headset, with the base. O.
Jest.
Dobra. Zegary są pomocnicze, odliczają w dół, a jak są pytania, to się zwykły zegar wyświetla.
Aha, okej.
Żeby tam mieć kontrolę godzina.
Jest.
Bo to pomocnicze, bo to. Tylko dziś prosimy o trzymanie czasu.
Tak.
To jest wyjazd.
Autobusy jadą.
Bo pokoje i autobus.
Yeah? Can I? Okay.
Jest aktywny.
It's nice
Na
to
początku sesji
be
pytań
free
proszę go
for the
włączyć,
nuclear
już nie
system.
wyłączać aż do końca sesji.
So that means
Dobrze,
also
dopiero jak skończy sesja pytań. I gdzieś tam z przodu, bo głównie
I'm not
pytania, nie
sure.
wiem czy pan zwrócił uwagę, idą
So that's fine.
tam z tej środkowej i w tamtej części są.
Tak, zwróciłem.
A, chociaż dzisiaj widzę, że się przesiadła część pytająca tutaj trochę, no ale to będzie druga osoba. To pan niech tamtą część, tą dalszą.
Dobra, czyli teraz jest...
Good morning, everybody. It's my great pleasure to chair this first session of this wonderful conference. There are two invited presentations. And the first presentation will be given by Makoto Koda from Tohoku University in Japan. And it's about the spin helix in semiconductor heterostructures. And we are very much looking forward to your presentation.
I should be punctual because our bus is waiting at 11:45. So, so I will start my presentation. So again, today I will talk about the control of the spin helix in semiconductor heterostructure. So my name is Makoto Koda from Tohoku University. So first of all, I briefly introduce where I'm from. So I'm from the Tohoku University in Japan. So this is a Japanese island. Here's Tokyo. Our university is here. Like the northern part of Japan takes like 1.5 hours by the bullet trains. And recently, the Tohoku University received the University of Research Excellence from the Japanese government, which means we will receive like $100 million a year for 25 years, which is a large amount, not for me, but for the university. And I should mention also that the former president, like Hideo Ono, Professor Hideo Ono, who is also pioneering like a researcher in the field of spintronics, he made the great effort to receive such nice designations. And now we are hiring the 500 researchers over the 5 years. So we will see what's going on in the next 5 years. Also in our campus, we have a new synchrotron like a facility system. Basically, this is focusing on the so-called soft X-ray around like a 3 giga electron volt. So that means that we can measure the light materials such as the oxygen, sulfur, or selenide. So that means that it's good to explore new material based on the 2D materials or oxide materials. So if you're interested in, please let me know. So our offices, my offices are around here, just takes like 15 minutes by walk. It's very, very convenient. Okay, then I move on to the scientific part. So in the spintronics field, many of you are involved. On the spin up, we utilize the spin up and the spin down as a two-level system in a classical way and also the quantum way. So classical way means towards the non-volatile memory, either spin up or like a spin down in the magnetizations through the magnetic tunnel junctions, spin orbit torque, and so on. And the quantum way means towards the spin qubits in the semiconductors. So the important thing is these two fields are complementary. These two fields has been complementary developed each other. So this is very important. And now the spintronics drives the two major markets, MRAMs and also the quantum computing. So recently, they're not only like a spin up and a spin down, but the spatial spin texture plays an important role in magnetic materials and also the semiconductors. So in the magnetic materials, so spatial spin structure means the spin or magnetic moment is spatially modulated. So this is a definition. Okay, in the magnetic materials, so because of the local magnetic moment and also the various types of the magnetic interactions such as like exchange, dipolar, Jaszowirc-Mollier interactions, so we have various types of these spin textures, magnons, domain walls, and skyrmions. And even in the magnetic material itself holds some special spin textures like chiral magnet, collinear, non-collinear, antiferromagnetic, and so on, and that makes the fascinating physics and also the device applications. Then how about the complementary field, which is the semiconductors? No local magnetic moment, no magnetic interactions, but there is plenty of physics in the spatial spin textures. So that's why I'm interested in this, like so-called relatively new frontiers in the semiconductors. So that's why today I will talk about the physics and also the functionalities of such helical spin textures in semiconductors. So first of all, I briefly introduce the advantage of these helical spin textures and how we can stabilize this in semiconductor systems. And then afterwards, I will show several experimental examples. Since this is this spin texture is regarded as the wave-like natures. So that means that we can make the multiplexing of the spin helices and also the interference. We can also transport the long distance of this helical spin coherence. And if you have a time, I will also mention about the electrical detection and also the material perspective. All right, so similar to the magnetic materials, there are spin textures of the electrons and also the nuclei in semiconductors. So one is the so-called persistent spin helix state, where the electron spins are coherently rotate without any external magnetic field and also the magnetic materials. And because of the SU2 symmetry, this spin texture is very robust against the spin-independent scattering. So that's why we can stabilize the spin textures in even in the semiconductors. So based on that, there's several proposals, such as the electron spin-based skyrmion lattice, logic operations. And if you have a helical nuclear spin in the nanowire structures, there is one proposal for having the exotic quasi-particles, such as the parafermions. So that means the spin texture is a key for novel physics and also the applications in semiconductors, similar to the magnetic materials. So in this semiconductor-based spin texture science, we have major two different areas. So one is the functional platforms, which means we can use such as spin helix structure as information carriers towards the logic operation or information filtering and even multiplex information transfers. And the other field is emergent physics. So that means such a spin texture itself becomes the origin of the new physics, such as the divergence of the quantum matrix under persistent spin helix state, and even P-wave superconductivity if you have a heterojunction with the S-wave superconductor and also the spin helix materials. So that means such a persistent spin helix is a gateway to explore the spin texture in semiconductor. Okay, so then the main advantage of this helical spin texture is to utilize the wave-like nature in semiconductors. So once we have such a helical spin patterns, then we can well define the wavelength. So that means that we can describe it by the sinusoidal functions. If we compare with the conventional like uniform spin polarizations, we can utilize not only the simple spin polarization is a spin up or spin down, but also we utilize the wave numbers on the phase, which is the intrinsic nature of the waves. So here is a dispersion relation of the electron spin helices. So this uniform spin polarization corresponds to the Q equals 0. So that means these two positions. But we can have many different or like various the wavelengths of the spin helices based on this dispersion relationship. So that means that we have some possibility to realize the new functionalities based on these spin textures. Okay, yeah. So then the fundamental like demonstration should be to show the wave-like nature based on this helical spin textures in semiconductors, such as the multiplexing of the different wavelengths of the spin helices or interference, and even transport of these spin helices so the long distance. So I will show the experimental data one by one in my talk. So before going to that, so first I will discuss about how we stabilize this spin helix in semiconductors. Okay, so the key ingredient is the spin-orbital interaction. So many of you already know the spin-orbital interactions. So when the electron is moving in one direction with the momentum p under some internal electric field, then this internal electric field is converted to the effective magnetic field. So that means the spins start to precess like this. So this is a description of the vacuum state, but we can also apply to the solid state. So that means basically electron spin feels the effective magnetic field without any the magnetic materials. Okay, so then what kind of materials we can produce towards the helix? We can choose the conventional or like 3-5 semiconductor heterostructure. This is the represented materials to show the persistent spin helix state. So the electron is basically confined in the gallium arsenide quantum well. So aluminum gallium arsenide is like a barrier layers. And once we have because of such a potential gradient, which induces the internal electric field, which is a perpendicular orientation, and our momentum is in plane. Because the effective magnetic field is the outer product of the momentum and the internal electric field. So that means that our effective magnetic field is also in the plane in this system. So because of the different origin of this internal electric field, we have a two spin orbit interaction in 3-5 semiconductor heterostructures. So one is so-called the Jaszowirc spin orbit interaction due to the structural inversion asymmetry. So that means basically such a potential gradient of the band structure induces the effective magnetic field. So the other one is the crystal field between the anion and the cation, and especially in the zinc blende structure. So this is so-called the Dresser-Haus type of the spin orbital interactions. And both of them contribute as the effective magnetic field. But the symmetry of the effective magnetic field in the momentum space is very, very different. In the case of the Jaszowirc case, the effective magnetic field is always the perpendicular to the electron momentum orientations. However, in the case of the Dresser-Haus type, the symmetry is completely different. So if you have one of these effective magnetic field in the semiconductors, what's happened to the spin dynamics? So basically, if you have one of the spin orbital interactions existed, then that induces the spin randomization or spin relaxation. This is because the electron is usually randomly scattered by the impurities. So that means electron momentum orientation is also randomly changed. Corresponding effective magnetic is also randomized. And in the end, the spin polarization is completely destroyed. So then, so far we have no hope to realize the stable spin textures under this effective magnetic field. But however, there's the sweet spot, which means if you have both effective magnetic field, Rashba and the Dresser-Haus effective magnetic field at the same time with the same strength. So that means that simply we add these two effective magnetic fields together, then total effective magnetic is no longer momentum dependent, but rather it becomes the uniaxial alignment like this with the modulated effective magnetic field strength. So when we look at the two different crystal, the momentum direction, like a ky, in the ky orientation, effective magnetic field on both parallel orientations. So that means the total effective magnetic field is enhanced. However, along the, for example, kx orientation, this guy and this guy is completely anti-parallel with the same strength. So that means the effective magnetic field is completely canceled out. So no effective magnetic field along these directions. Then what happens when we excite the perpendicular electron spins by optical excitation or electrical spin injection? Since this electron spin fills the effective magnetic field, so it starts to precess. Along this ky orientation, where we have the largest effective magnetic field, this spin precession takes place like this. However, in the kx orientation, there's no effective magnetic field. So that means the initial spin state, up spin state, is preserved like this. And in the end, we have a nice spin coherence in entire momentum space. So that means even though the electron is randomly scattered, but the electron spins coherently rotate, so which is so-called the persistent spin helix state. And this is our a starting point to use the electron spin textures in the semiconductors. So here's some cartoon. This is some animations to show what's going on. So basically, when the electron is moving to the one directions, the electron spins are coherently rotate like this. So that's why we can regard this as the wave-like natures. Okay, so now we focus on the 3-5 quantum well, but such a persistent spin helix state is existed in the various different materials, such as the 2D materials, monolayer SNS, oxide interface, and even though the semi-metals. So that means basically the spin helix is ubiquitous in your materials. So please check your materials whether your material also holds such a very nice spin textures. Okay, so then the next step is how we detect or how we excite these electron spin textures in the semiconductors. So basically, we use the so-called pump probe method. So time-resolved curve rotation measurement. So we use the mode-locked tie-sapphire laser, and we use the circularly polarized pump beam to excite the electron spins in 2 legs. So we have a very, very tiny spot with the uniform spin polarization. And because of the electron diffusion, after the excitations, each spin feels the effective magnetic field and the spin precessional motion is evolved. Then we can detect with the linearly polarized probe beam with some time delay for the spin dynamics. And also by scanning the mirror, we can also map out the spin textures. So we use the gallium arsenide, aluminum gallium arsenide conventional quantum well structure, but we designed to satisfy the persistent spin helix condition, which means the rush bar is almost equal to the Dresser-Haus spin orbit effective magnetic field. Okay, so here's one example. So we excite with the Gaussian profile of the uniform spin polarization at t equals 0. And after that, because of the electron diffusion, the electron spin precessional is evolved. And we see the very nice a spin up and spin down and spin up these a precessional motion. This is the simulation. And this is actual data with different delay times. So first we have the Gaussian spin polarization profile, but because of the electron diffusion, we have such a spin precessional motion. and we can well define the spin helix wavelengths like this. The important thing is this spin helix wavelength is solely determined by the effective field strength. So PSH, effective magnetic field strength, determine this spin precessional pitches. Okay, but when we look back to our dispersion relationship, we can also have a different spin helix wavelengths. Then how we access to not only this wavelengths, but also the many different wavelengths. Then we have another idea to excite the arbitral spin helix in semiconductors by using this so-called spatial light modulator. So spatial light modulator is basically, it's simply talking, this is like a liquid crystal. So that means that in each pixels, we can control the optical retardance. So that means before going through this SLM, this is our laser beam, and the optical polarization is only all one direction. But through this spatial light modulator, we can design any types of the optical polarization, and because of the optical selection rules, we can imprint this optical polarization to the spin system. So here is one example. So this is our laser spot just before going to our samples. So diameter is around 100 micrometer, which is relatively large. And then we have a nice stripes of the right circular polarization, the green one, and the left circular polarization is a pink one. And then because of the optical selection rules, we can transfer the spin angular momentum to either spin up or spin down like this. So we can basically, with this technique, we can excite any types of the spin helix in semiconductors. So here is examples. So this is a plane wave, and also we change the wave numbers up to 1.1 inverse micrometers. And this is the initial spin helix state, and also we measure their dynamics. So their dynamics strongly depends on the wavelength. So from these data, we can also extract the lifetime of each spin helices in the system. So here's a summary of our lifetime, the spin helix lifetime, as a function of the wave numbers. So there is such a helical spin lifetime strongly depends on their wavelength. So here is a longest wavelength, longest lifetime corresponds that the excited optical spin helix is completely matched to the spin precessional motion induced by the effective magnetic field. So that means a very coherent rotation is maintained. However, if you have the larger or shorter wavelengths or longer wavelengths, this wavelength is not matching to the spin precessional motion induced by the effective magnetic field. Then the diagonal parallel type spin relaxation takes place. So that's why the lifetime is getting shorter and shorter in these regions. But by utilizing this stronger anisotropy of the lifetime, we can make some spin helix filtering based on that. And also, once we excite any types of the spin helix, we can excite not only one, but also the multiple spin helices in semiconductors. For example, I take the one spin helix with the longest lifetime, and the other one is a shorter lifetime around here. Then, so we prepare the two different types of the wavelengths, and we multiplex these wavelengths together, and we program it into the SLM. Then we first excite the two different spin helix states simultaneously at t equals 0, just like optical excitations. Then also we check the spin dynamics. So after some time, like 200 picosecond, we only observe the most stable spin helix because of this strong spin relaxation and anisotropy, one of the helices decays faster than this. So that means we excite the multiple spin helices, but these are completely independent and we can control independently. So which is a very, very good thing if we want to use this spin helix as an information carriers. Then next is once we have multiple spin helices, then next step as a wave nature is the interference of each spin helix. To do so, we pump not only like one position, but also the multiple positions. So in this case, we excite one spin helix here, and the other one is here. And if we excite these two spin helices simultaneously, there is the spin helix, the interference at this position, and because of it's the same like spin polarizations, we have a constructive interference. However, once we change the spin polarization from up to down, so that means the pi phase change. So then there is a destructive interference at this point. So we can do this in more sophisticated way. So that means we change the relative position of the two spin helices. So like this. So first we fix the first spin helix in this position, and we change the relative position of the second excitation here. So that means we have an interference effect between these two spin helix. So when and this is a simulated result based on the Monte Carlo spin dynamics. So when we look focusing on this interference area like this, these red lines is nicely reproduced in the simulations. So this means we can really precisely control such an interference through the relative phase or relative positions. So then we can use this interference effect to some fundamental logic operations. So this is so-called the majority voting, or more precisely, it's a majority logic operations. So then next, I excite not only 2, but also 3 at these corners of the triangular positions. So this is a simulated result. And we detect a spin helix interference at this center position. So that means simply we scan the car rotation microscopy on this horizontal axis. So then what's the definition of the majority voting or majority logic gate? So definition is basically how many spin spots are either spin up or spin down. So in this case, all the spot is a spin up, so majority is a spin up. But this one is all the spot is a spin down, so majority is a spin down. Then what about in between? For example, here, one of the spot is changes from spin up to the spin down, but still the majority is a spin up. But in the case of these 2 points are spin down, the majority turned to be the spin down. So this is the kind of a majority voting experiment. And why this is important? Because this majority logic operation includes 2 logic gates already. One is the AND gate, the other is the OR gate. So if we want to really use such a spin helix as information carriers, this a majority operation would be the first step to show some gate operations. So when we look at the experimental data, so if we excite these 3 spots with the spin up, then of course we have a nice positive polarization at the center positions, which is reproduced by the simulations like this. Once we change one of the spot to the spin down, still we have a small positive spin polarizations. But if 2 of them is a spin down, then it goes to the negative polarization. And of course, if the 3 of them is a negative spin downs, then we have a negative large polarizations. So that means because of the precise control of such a spin interference or spin helix interference, we make the fully deterministic output through the linear interference effect. And this is equivalent to the majority logic operations. Okay? So once we can do some let's say logics, then of course we can also transport this information to the long distance. So we also apply the bias voltage in our sample to transport how long we can transfer these informations. So we make such a wire structure based on the gallium arsenide, aluminum gallium arsenide quantum well. Our wire width is relatively large, from 20 micron width down to the 5 micron meter width. So then we apply the bias current from left to right, and we transport the excited spin helix to the one directions. And then we map out with the car rotation microscopy. Okay, so first I showed the relatively large the width, wire width samples. It's a 20 micron width. So we excite the spin helix at this position, and we apply the bias current. Of course, we increase the bias current, we can transport such a spin helix coherence for the long time. And based on the exponential cosine functions, we can extract how long this is transported. So it's so-called spin transport length. So this spin transport length, here is a spin transport length as a function of the drift current. And you see the sudden increase of this spin transport length up to 100 or more than 100 micrometers. So when we turn to be the narrower wire width, then the situation is drastically changed. So basically, once we apply the large drift current, we can transport over the 200 micrometers, which is a relatively long distance if we consider the spin coherence. So when we look at the other materials or other systems, so here's a comparison with the other spin coherence transport. So this is the same gallium arsenide, but the bulk and gallium arsenide, this is a very similar structure of the gallium arsenide quantum well. But as you see here, and this is our result. So as you see here, so the transport length is still limited around 50 micrometers. So our case is over 200 because of the persistent spin helix state, which is very robust against the spin-independent scattering events. When we compare with the king of the semiconductor, silicon, then the silicon holds the very small spin orbit. So that's why the spin polarization is transported over the 300 micrometer, which corresponds to the thickness of the silicon wafers. But if we can induce some spin coherence because of the small effective magnetic field, that they need the external magnetic field. So here's another example of the quantum dots based on the gallium arsenide. So they grow the quantum wire and this edge. Then by using the Sarkos acoustic wave, which means basically the potential is modulated by this Sarkos acoustic wave, then they can transport the so-called moving quantum dots. The quantum dot is moving from one place to the other. And then they see the spin precessional motion or spin coherence, but still limited to the 100 micrometer or 120 micrometers. So that means our result is relatively long spin coherence transport because of the suppression of the spin relaxations. Okay, so far we are focusing on the 3-5 materials, and we do the optical excitation and the optical detection. But there is several, so here's the material candidate. Some of them is wider band gap materials, some of them is even semi-metals. So we cannot apply to the optical excitation and optical detections. So how we can overcome this problem? Then we came up with idea to use the magnet transport measurement to detect the helical spin lifetime. So more precisely, we use the quantum interference effect, or a weak localization or weak anti-localization measurement. So quantum interference effect is similar to, it's as follows. So suppose, so this is our semiconductor materials, gallium arsenide. These dots correspond to the impurities. So that means when the electron is moving to here, the electron is scattered, and there is a possibility to scatter and go back to the original point. And there is another possibility two take the opposite path, exactly the opposite path. So that means these two paths interfere each other at this original point. This is very similar to the, for example, like Aharonov-Bohm ring or Altucher AAS oscillations. So because without the spin-orbit interactions, since this interference becomes constructive due to the orbital phase, so the conductance is decreased because of the weak localizations. But once we apply the perpendicular external magnetic field, this localization is destroyed through the vector potential. So that means the conductance is increased, so-called this is a weak localizations. However, when we have spin-orbit interactions, also we need to take into account the spin precessional motion or spin phase. Since the a spin phase for the clockwise orientation or anti-clockwise orientation is the opposite phase, so that means the interference becomes the destructive. So the corresponding the conductance is rather increased. But again, once we apply the external magnetic field perpendicular to this, then this the phase shift is compensated by the vector potential. So the conductance is decreased, but increases again. So this is so-called weak anti-localization. So based on that, we can also detect the helical spin lifetime. So here is the quantum collection of the conductivity. And there is two terms described by the digamma functions. So one is the helical mode and the homogeneous mode. And in these digamma functions, actually there is a helical spin relaxation rate, and also the homogeneous spin relaxation rate, which corresponds to these spin textures. So that means by analyzing the quantum collection to the conductivity in the vicinity of the persistent spin-like state, we can still evaluate the spin lifetime. So that means we can apply not only like 3-5, but also the various different materials like narrow gap band materials or even the oxides. So to this end, we check this idea with the conventional gallium arsenide materials because we can compare with the optical measurement and also the simulations. Okay, so here's again the same gallium arsenide based quantum well, and we also put the gate to control the spin orbit interactions. So here is observed like a weak anti-localization signals with the different carrier density, which corresponds to the different bias gate bias voltage. So by changing the carrier density, the effective magnetic field is close to the persistent spin-like state, which corresponds to the very weak anti-localization because the spin localization length over time is enhanced. So then here is the result of the inverse of the spin helix lifetime as a function of the carrier density. So that means the smaller value reflects the longer lifetime. So this is a spin helical mode, and this is a homogeneous spin mode. Then the circular plot corresponds to the experiment from the weak anti-localizations, and this square corresponds to the simulation based on the optical measurement. So which are well agreed each other. So that means based on such a magnet transport measurement, still we can access or we can explore the spin helix the properties in the materials, semiconductors. So okay, then finally, rest of my time, so I will briefly mention about the material perspective. So again, here is a proposed materials to satisfy such a spin helix state. Then what's the difference? Basically, difference is the different spin orbit strengths. So here is a summary of the strengths of the spin orbit interaction in terms of the wavelengths of the spin helix. If the effective magnetic field is stronger and stronger, then induced, but the wavelength is shorter and shorter. So when we look at the wavelength, typically in the gallium arsenide case, the wavelength is around like 10 micrometers, which is relatively long. But yeah, when we compare with the nanoscale logic devices, 10 micron is huge, right? So we need to explore the other materials. Some of them shows the very short, like a spin helix wavelengths, like on the order of the, like a 10 nanometers or so. So here's a summary of the wavelengths of the spin helix as a function of the strength of the spin orbital interaction. We nicely see it's aligned in the one lines like this. So that means now we are focusing on, well, we are doing the experiment in the 3.5s. Typically, the wavelengths corresponds to the 10 micron to down to a few micrometers. However, in some of the materials, oxides, or especially like a 2D materials, these materials shows the very, very short the spin helix wavelengths, which would be the promising to do some logic operations in the future. And actually, we are working on this tin sulfide, and I hope to show the spin helix dynamics in the near future. Okay, with that, I summarize my talk. So today, I showed the control of the spin helix in semiconductor. Not only like magnetic materials, even the semiconductors, that we can induce or we can control the spin texture. So I hope also we can make the hybrid structure between the magnetic material spin texture and non-magnetic material spin texture in the future. Okay, then here's acknowledgement. So this is our team, and we have a very nice collaboration with the other people, and especially I'm deeply appreciated my collaborators and also the friends in the Poland. With that, thank you for your attention.
Thank you very much for this really fascinating talk.
Thank you.
Papers open for discussion, questions. Yeah.
I also very appreciate your talk about persistent spin helix, since my group is working on optical analog of this persistent spin helix. And I wonder if the concentration of carrier also plays a role with the observation of spin helix. I mean that we were trying to, or we have observed this persistent spin helix, but we noticed that the best contrast we got only if we excite our analog, optical analog, on the very bottom of those two paraboloids. If
yes.
we excite it a little bit higher, which will correspond to higher Fermi energy, the contrast is weaker. Can you comment on it, how it looks in real experiment?
I see. Yeah, that's very, very important. So that means basically let's see. So I have a spill bit. Basically, so in this case, I simply describe with these two effective magnetic field. But actually, there is a additional term, so-called the higher order Dresser-Haus term, which breaks this symmetry. And that depends on the carrier density. So as you pointed out, if we increase the carrier density, not only this symmetry, simple symmetry, this is so-called the linear term, but also the additional cubic term contribute to this symmetry, which breaks the nice SU2 symmetry. So we have to be very careful to the carrier density. So that's why we put the gate to precisely control not only like a spin orbit field, but also the carrier density as low as to not be negligible, but as small as the cubic term to this spin dynamics. Yeah.
Thank you. Further questions? Then, okay, I have a question.
Yep.
So actually you mentioned scattering. So how sensitive are these effects to material quality, and for gallium arsenide, like how could you, do you need the samples with the highest mobility? Do you need 10 million centimeters squared per volt seconds, or
Yep.
how robust is it?
Okay. Yeah. So far our like a two-dimensional electron, for example, mobility of our structure is 1 million, like mobility. But we can still measure the such a nice spin helix on the order of let's say 100,000 mobility. So the one with a lower mobility than the 1 million, but still we see. Because basically the such a spin helix or like a spin dynamics is the or spin localization is independent of the spin independent scattering. So that means the simple impurity scattering does not affect too much to the spin dynamics. But of course, there is a spin evolved like a scattering event. And then in that case, this spin helix pattern is destroyed. So that also depends on which kind of a scattering, like a phonon scattering or a chiral phonon scattering and so on, that evolved into this spin helix state. So in this point of view, the temperature dependence of this spin helix state is very important. And so far, in the other groups, they observed such a spin helix up to 200 or 220 Kelvin, but not in the room temperature. Yeah.
Thank you.
I have a question. Because on the first transparency, you showed that you need to have Drescher house and Rashba field cancer. So I understand that you have, because you mentioned many materials, let's say, and how do you, and I understand, for instance, just apply electrical field, you can control Rashba just to get the canceling. Yes, but let's say that, so how can you, so in other materials, like gallium arsenide, let's say I understand, you have quantum well, you have electrical field, you bend and you can control and make it equal, and you have nice long helix lifetime.
Yep.
And now other materials, how do you, why do they, they have cancel? Do you also apply electrical field or what?
Yeah, that's a very good question. So maybe I should show some, let's see, some data about the different crystal orientation in the 3-5s. If I have some data, let's see. Okay, so it seems not. Okay, so maybe this one. So basically, the other materials, basically some materials, for example, 2D materials shows only the Dresser house. Let's say like a spin orbit feed from the bulk inversion asymmetry, and so this corresponds to the Dresser house in terms of the 3-5. And for example, 2D material, for example, SNS, the tin sulfide. So this shows the perpendicular effective magnetic field orientations only from the spin orbit of the crystal field, not the Rashba. Only like a Dresser house contributes to realize such a persistent spin helix state, which is very similar to in our like 3-5 materials. For example, like a 110 crystal orientations, which is also very, very good like a crystal orientation in terms of the spin orbit. So in the 110 crystal orientation, only the Dresser house, but still because of the symmetry, they can realize such a nice helical spin textures. So this is very similar to the other material, 2D materials or like a bulk materials because of the like a crystal symmetry, which satisfy some kind of this like a symmetry. But if we make the interface, then we need both Rashba and also the Dresser house.
Okay. Thank you very much. I think for the sake of checkout and departure, we will move the further discussion to the coffee break. So thank you very much once again. So this second invited talk today in the morning will be given by Renata Putkute, and this will be about strategies to include bismuth containing 3-5 semiconductor compounds for near-infrared micro lasers and the challenges and
Do you hear
strategies.
me? It's okay? Good.
Okay, so thank you, Morris, for kind introduction. I would like at the beginning to thanks organizers for inviting me to this conference. Ewa, Piotrek też. Dziękuję bardzo. This is the 5th time, so 4 times I was as a postdoc student from Institute of Physics, Polish Academy of Sciences. And today I represent Center for Physical Sciences and Technology. All skills learned in Poland, we transferred to Lithuania. Material is different, but I'm very happy that this 4 years postdoc was very, very successful, very important for me, and I'll still keep my relations with Eva and Piotr, and we exchange our ideas and we collaborate. Okay, so you can find in my topic more exotic compound, bismuth A3B5 compound, and the second very important word in the topic is challenges. I think that challenges are most important thing in order to make a progress. So I prefer to have challenges in order to achieve progress and to teach my students how to do. Okay, so how to achieve in time beautiful results, how to explain and how to understand. We Lithuanians are very crazy about lasers, and it's a very good thing for me because students like lasers and they come to my team. I have a huge bunch of students and I have a possibility to select the best. So lasers are of 2 types in Lithuania. The first type is solid-state lasers, and our colleagues for light conversion are presenting the stationary, very powerful, and etc. lasers. And I am a woman of micro lasers, and these micro lasers are can be applied in various areas. So let me introduce our team. And I said that team is young, and I still think that the best chance to achieve something is to generate into the strategical session a crazy idea, to write a proposal, to obtain money, and to do the experiment or achievements in time. So people are young, very... Okay. No. Okay. So people are young, very thirsty of knowledge, and as you can see from this circle, we overlap all activities, starting from technology, some not maybe theoretical, but some modeling things, experimental area, and we are very successful also in applications. Even we started to apply some machine learning methods in order to see what we can't see by naked eyes and explain some results or some crazy ideas, some crazy origins or different effects. Doesn't matter that we are fully involved in all activities, we still have partners abroad, and we collaborate, especially with Taiwanese people who are very interested in our structures. and have an idea to remove the substrate from the structure from the substrate and to integrate our lasers on silicon carbide platform. So we are happy to collaborate and to have good results. Okay, so let me introduce the area. So the area is near infrared, and we selected near infrared due to a simple thing. In this area, we have many applications, starting from telecommunication, quantum communication, photonics on silicon integrated, also some medical applications. This area is also very crowded by molecules surrounding us, and we can propose some microlasers targeted to these molecules. And it must be stressed that in this area we have very well developed and very accurate detectors. So lasers are necessary for this area. And my topic is more exotic semiconductor compound from this A3B5 family, and we are focusing to gallium arsenide bismuth. So exotic is based on that we combine gallium arsenide and also gallium bismuth, virtual compound which doesn't exist in nature and also in our laboratories, but theoretically is proved that this material is semi-metal, and can be incorporated to gallium arsenide. So we combine gallium arsenide together with gallium bismuth and have gallium arsenide bismuth. In this compound, bismuth substitutes arsenic. And gallium arsenide can be grown easily on gallium arsenide platform. Also, we can grow gallium indium arsenide bismuth on indium phosphide platform, quaternary compound, and by this compound cover the wavelengths from 6 micrometers up to 6 micrometers on indium phosphide platform. Moving on indium arsenide and gallium antimonide, 2 ternary compounds are possible, and these compounds can cover from 6 micrometers up to 12 micrometers. It means that this large bismuth family can cover applications of lasers, microlasers and detectors from 800 nanometers to 12 micrometers. And why we like these materials? There are 2 main properties. The first one is the much larger band gap decrease by introducing several % of bismuth to gallium arsenide, up to 90% of millielectrons for 1% of bismuth. And this ternary or quaternary compound is less sensitive to temperature. It means that band gap is stable in wide temperature range. And for ternary compound is also very important thing that with introduction of 10% of bismuth, we increase the spin orbit splitting, and it becomes larger than energy band gap. And this property is very important for application in lasers by reducing Auger losses. From these losses, laser diodes suffer now. Okay, let's move to the challenges. The challenge is that bismuth is much larger than arsenic and can introduce some lattice distortion. It was also demonstrated to indium gallium arsenide in the picture that by introducing some percent of indium to the gallium arsenide lattice, we have lattice mismatch dislocation net, which is responsible for the reduction of intensity of luminescence. So these areas of crossed dislocation net, you have reduction of intensity, and it could be the origin of luminescence decrease and killing of lasing property. So in this case, with larger decrease of band gap, we need to introduce less of bismuth than indium and to overcome this problem. And that we can do by using molecular beam epitaxy system. I said that bismuth is very large, and bismuth also has a property to segregate to the top of surface. It acts as a surfactant and covers like a wetting layer structure and enhances the crystalline quality of ground layer on the bottom. So in order to introduce bismuth, we need to reduce significantly growth temperature. It means that from usual gallium arsenide 580, we need to reduce the temperature sometimes up to 200 degrees centigrades. Then bismuth is in the lattice, and we can keep. But such low temperature originates generates creation of the various defects, and defects kill luminescence. So at this temperature, we can obtain very weak luminescence and no chance to make a laser from this material. The second thing, which is very important, is bismuth segregation to top. And in order to keep bismuth in the lattice, we need to reduce significantly arsenic flux. Arsenic flux and gallium flux must be equal, and it can generate some droplets on top, because it's very difficult to keep the balance between gallium and arsenic. So always we have some droplets on top, and it's not good for applications. Let's analyze how we can grow gallium arsenide bismuth. Let's start at the beginning from the thick layers, and usually on the left there is a main technological map used by scientists in order to grow gallium arsenide bismuth thick layers or quantum wells. So you can see that it is a very narrow window of arsenic to gallium ratio to introduce bismuth. The same is with bismuth flux. The lack of bismuth flux initiates roughening of surface. The excess of bismuth flux always makes droplets and introduces less of bismuth. So there are two limitations, one from side of gallium to arsenic to gallium flux, and the second bismuth flux. So usually people are operating from 1 to 1.2 area of flux. Also, technologies, we like to talk not by fluxes, but by pressures, beam equivalent pressure. Because we are measuring beam equivalent pressure, not the flux. Flux must be recalculated. So using beam equivalent pressure ratio, it's possible to grow beautiful gallium arsenide bismuth layer when the ratio is from 4.5 to almost 5. So all people are using this region, and the intensity of luminescence is not very impressive. So in our experiment, we decided to check the area from one side and the area from other side. So our region is from 1 to 6. In the area from 5 to 6, we realized that we grow pure gallium arsenide, probably a little bit of worse quality than usual high temperature gallium arsenide. And in the area of 4 to 5 beam equivalent pressure ratio, we have good intensity of luminescence, good quality of gallium arsenide bismuth, but depending on bismuth, we can have very enhanced luminescence or very weak luminescence. Reducing the arsenic to gallium ratio, we also reduce the intensity of luminescence, and finally, by reducing even more arsenic to gallium ratio, we realized that there is a second window, perfect for very high luminescence. I'll show now how looks various surfaces of layers grown at different areas of beam equivalent pressure arsenic to gallium ratio, and how it depends on bismuth flux. So this very complicated maps demonstrate that there are many, many things to do with bismuth. And looking to these different 4 areas, we can realize that in all regions, in all windows, we can have perfect crystalline quality of gallium arsenide bismuth, but the surface looks different. Even in this area of 3 gallium arsenide bismuth, we can grow bismuth layer with some periodically oriented pockets of bismuth nanocrystals. So it means that this large map shows different ways of different nanostructures growth, starting from quantum wells and finalizing with thick layers, nanocrystals, nanorods in planes, and etc. So the first window is very important because it doesn't depend on bismuth flux. We always have a very high intensity of luminescence. And from the XRD picture, we can tell that in this region, the mechanism of the growth is different. So gallium flux is very high in comparison to arsenic flux. And first minutes of the growth, we are growing in usual growth rate, gallium arsenide bismuth of perfect quality. But at the same time, gallium is accumulating on the top. And in the one moment, we have fully or most fully covered by gallium layer, and bismuth can't be introduced. So in this case, we have 2 layers. One is of about 5 nanometers, and second is free of bismuth, about 30 nanometers. So comparing crystallinity, comparing surface, comparing optical properties, we decide that this region of about 4.5 is perfect for thick layers. So 100 nanometers, you can grow the layer which is not relaxed, fully strained with the same bismuth incorporation. In the first region, we think that this region is the best for the growth of quantum wells. And our future devices we are done on this area using this region. Okay, since gallium arsenide bismuth is very exotic material, virtual plus usual semiconductor combined 2 in 1, we also need to evaluate the efficiency, because for application of quantum wells in the gain area of device, it's useful to know the efficiency of material. And our first approach demonstrated that taking into account ABC model and changing C compound for very hardly disordered material, we can obtain the efficiency of millipercents. So nothing, nothing. And this is a challenge. We need to find a way how to apply this material, because we are stubborn and we need to show that almost always we can overcome nature and to have a good tool laser. Okay, so for this we have several recipes. Nothing new, all was done, but just we need to remember, apply, and obtain some result. So the idea was taken from parabolic profiles, parabolic barriers, and in very highly disordered material, we need to excite barriers in order to collect carriers and to insist recombine in quantum well. So usually for gallium arsenide bismuth, we use the parabolic barrier of aluminum gallium arsenide. It was demonstrated that the best composition is about of 30% of aluminum in gallium arsenide bismuth, and pumping barriers, we insist recombine carriers in quantum well. It was done not, how to say, it was done a little bit implementing different project. The calculations were done for terahertz storage, but applying these parabolic barriers for bismuth, we realized that we have 100 repeatability of luminescence of optical properties and minimum 50 times increase in luminescence. So it was perfect result for us. And this profile was done just by growing molecular beam epitaxy by decreasing aluminum source in analogous method. Not in digital method, but just the analogous method, calculating some steps, profile, shape, and etc. And second recipe for very low temperatures, how to obtain the perfect quality of material was adapted from a Japanese paper where migration enhanced epitaxy method was used for aluminum gallium arsenide growth. They demonstrated that even at 200 degrees centigrade temperature, growth of aluminium gallium arsenide, which is very capricious to temperature and to arsenic flux, it's possible to grow perfect aluminium gallium arsenide exhibiting very high intensity of luminescence. And method is based on supply of different sources, group 3 and group 4 separately. So group 3 at very low temperature is very, not diffusive. Migration is very low. So we need to make an interruption after supply of group 3 in order to gallium can find the real site in the lattice. Then we can supply arsenic and bismuth after gallium and etc. So layer by layer, we calculate how many sites we have on top, and we cover and cover and cover, and even growing at 160 degrees centigrade, we had a huge amount of bismuth, more than 10%, and photoluminescence from this material. So combining this, parabolic quantum bells, we can insist our highly disordered bismuth to have a good photoluminescence emission. Okay, and third thing is what we can do with these droplets, because it's difficult to avoid these droplets, and the idea came from the paper in Physical Chemistry Journal about the colloidal bismuth nanoparticles. It was demonstrated that these particles are very useful for application in 1.55 micrometers telecom range. It was demonstrated the absorption, and we decided that we also can do from this droplet bismuth quantum dots. And we will have not only gallium arsenide bismuth quantum wells, but dots in the well. And our theoreticians calculated that bismuth in general is semi-metal in bulk. Then reducing the size of bismuth cluster up to 60 nanometers, bismuth comes semiconductor, but indirect bandgap semiconductor. And then reducing even more, less than 60 nanometers, we can have direct bandgap semiconductor. So it means that we need to grow quantum wells with thickness less than 60 nanometers in order to have a controlled diameter quantum dots of pure bismuth in gallium arsenide bismuth. And the idea is to grow huge amount, to put huge amount of bismuth to gallium arsenide bismuth, then anneal due to segregation to organize quantum dots, and have a good pure with sharp interfaces gallium arsenide bismuth quantum wells with pure bismuth quantum dots. And it was demonstrated in our paper with the aluminium arsenide barriers, and luminescence was also observed in 1.3 micrometers. But in general, pure aluminium arsenide is a bad barrier for gallium arsenide bismuth. It's too high barrier. And we need to think how to block bismuth into the well using gallium arsenide barriers or aluminium gallium arsenide. And two different things we have done using parabolic profiles with aluminium gallium arsenide barriers, and second, also parabolic profiles, but with very thin aluminium arsenide tunneling barriers in order to block bismuth into the quantum well. And it was successful. We were happy. So now we have 3 recipes how to organize gallium arsenide bismuth quantum wells, and also probably for the second wavelength, how to make bismuth quantum dots in these wells. This method was described like alternative method to Stransky-Krastanov quantum dots organization method, method like bismuth segregation method. So we investigated all thermodynamical possibilities, how to grow gallium arsenide bismuth, how to fade with bismuth excess, with gallium droplets, and etc. And we realized 2 types of lasers, micro lasers. Started we in 2014, and the first attempt was demonstrated that 3 quantum wells of gallium arsenide bismuth in the first window can give us the lasing at 1060, but you can see that light intensity or power was also 0, nanowatt power. So something was wrong, and during these years, during this thermodynamical investigation, exploring, and etc., now we did the second type of laser, improved design of laser with reference of aluminium gallium arsenide laser. And we include rectangular quantum wells and also parabolic quantum wells, and we compared the results. So this slide demonstrates the results of our ternary partnership project devoted to the pulse oximetry device, so 800 nanometers classical material laser diode and 1100 bismuth laser diode in order to have the same penetration depth and less procedures for calibration. So you see how it looks, the design of quantum structure, and by changing composition of quantum well and thickness of quantum well, we can have different lasing of aluminium gallium arsenide or gallium arsenide lasers in the range from 780 to 800 nanometers, what is perfect for pulse oximetry. Okay, the second type, laser diode with gallium arsenide bismuth quantum wells, also rectangular and empty picture. Okay, so for with parabolic and also rectangular quantum wells. It was demonstrated around 1100 nanometers lasing from rectangular quantum wells. And let's compare how it looks. So rectangular quantum wells in aluminium gallium arsenide and parabolic quantum wells in aluminium gallium arsenide. So it's clearly seen that the spectrum is better, much impressive using parabolic barriers around quantum wells, rectangular quantum wells, and also power is similar. Threshold current is a little bit lower for parabolic. Also, we observed that using parabolic barriers, we can use a lower number of quantum wells. And we checked, we tested our aluminum gallium arsenide quantum wells in integrated optics company just to transfer to company product, and we were surprised, and they also were surprised because we have no possibility to measure line width in our laboratory. The line width was even less than 5 picometers. It means that our MBE is powerful to compete with industrial partners, and we are happy. And then we transferred the same technology to gallium arsenide bismuth based material LEDs, and you see on the left rectangular quantum wells, and on the right parabolic quantum well laser diode parameters. It's clearly seen that by using a parabolic profile for 3 quantum well surrounded by this parabolic profile, we can reduce significantly the threshold current, what is very important. In bismuths, it's one of the most important parameters we need to improve in comparison to rectangular quantum wells. Also, what we did, we polished or we tinned substrate to manage with heating, because highly disordered material with some design of laser diode has a very huge amount of heating, and it's necessary to remove this heating very fast. So black curve shows how significantly by thinning of substrate we can reduce the threshold current. It's a very good sign for us. And also you can compare how looks the power measurement of rectangular quantum wells and using parabolic profile. So increase more than 10 times. I think it's a very good approach for this type of material. Okay, by introducing more of bismuth, it's difficult to obtain longer wavelengths. And the reason is that we still need to fade with gallium and bismuth. Some liquid which can vanish our quantum wells. And in this case, in laser diode, it's a very huge difficulty. So we need to change the design of laser. And the idea is to switch from electrically pumped laser to optically pumped. Optical pumping allows us to obtain the light from the surface. And design of such laser is Bragg reflector on the bottom and quantum well stack on top, covered by window layer. So the idea is to excite all these quantum wells by exciting barriers and obtain very high power. So these Wechsel type lasers are very powerful, and they have two main difficulties. The one is that we need to have a very good geometry for extraction of light. And the second is that we need to have a very good large surface, because with scaling of area, we can increase the power. And indium gallium arsenide demonstrate that it's very difficult to obtain near infrared in this type of lasers due to indium generated dislocations. And our proposition was done by combining quantum wells in pairs and having a larger barrier to remove this, to kill this lattice mismatch dislocations. And our, I'm finishing. Okay, and our measurements demonstrated that we can reduce in such type lattice mismatch dislocations, and even with indium gallium arsenide and gallium arsenide bismuth obtain the lasing in near infrared. Okay, how it looks on gallium arsenide bismuth threshold of lasing, and also 12 quantum wells lasing in indium gallium arsenide bismuth. Okay, the temperature and power excitation measurements demonstrated that bismuth VCSEL is stable in very high power range, and it's a good thing for us and good news. For future, we would like to combine not only quantum wells, but also wells and dots, declares and dots, and investigate even more this exotic material. With this, I would like to thank you. I think that idea that we always can find some unusual recipes to fate with nature and to achieve and to face these challenges and to achieve results you want. So my wish is to you, never tell no. Thank you very much. And thank you, our company.
Thank you very much, Renate, for presenting this super interesting material system. Do we have questions? Yeah.
Thank you, Renate, for a beautiful talk. My question is about the size of these quantum dots. Because when I look on the different region, it looks like that you can control a little bit this size, and this is it influence on the intensity of the lighting?
Yeah, quantum dots can be, there are two limitations. One limitation is the barrier material, and bonds between aluminum and arsenic are much stronger than gallium and arsenic. Bismuth goes through gallium arsenide like water, you know, through the system, and you need to have a good barrier to block the bismuth in the quantum well, and even 1 nanometer of aluminum arsenide is enough. Second thing, you need to grow quantum well thickness in order to have specific diameter of quantum dot. Yeah, and in case of for example, of this thing, you have various quantum dots, or not quantum dots, even nanocrystals. But if you want to have one kind of quantum dots, you need to block bismuth. In this case also, you have a disc shape quantum dots. In upper slide, in upper pictures, you have randomly oriented spherical quantum dots. Yeah, so there is a possibility how to control orientation and
One short question still.
Okay,
Two
so
very short.
very quick question concerning this optical excitation. Does it depend on the wavelength? Because you've been using this green laser, and if you change it to, I mean, can you increase the efficiency of this lasing just changing this?
Yeah, by changing design of laser.
But not exciting wavelength?
No,
No, okay.
no.
I have a question. Is there any reasoning for using parabolic potential, or was it just you discovered that it helps to get lower current?
No, no. We didn't discover, we just applied earlier ideas of laser diodes. In order to have a more efficient laser diode, you need to have a Grinch type, step-like laser diode in order to collect all the carriers and recombine in quantum well, not in the barriers or in the waveguide. It's usual type, well known, and this was just adapted just to insist recombine carriers in the quantum well.
Is parabolic shape
Yeah.
important, or you can just have linear, for instance?
We can have linear. If we try to have a linear triangle quantum dot, it must be even better than parabolic, but my student didn't succeed to prove this. But yeah,
Okay,
it will be, yeah. This shape, parabolic or triangle, is very important, and triangle must be even better.
Okay, let's thank Renata once again. And before we go to the coffee break, there is an announcement.
So I just wanted to remind you that we ask you to check out by 11. This is the requirement from the hotel, so that's very important. You can store the luggage in the grotto. Now you just pass the reception desk and go to the right. And another very important information, please, it disappeared. Please be at 1:45 at the bus so that we can proceed smoothly with the departure. And this means that you will have today you have a bit less time for lunch, but we hope that everything will be okay. So thank you very much.
Podzielcie się.
We are testing.
Test, test, test. Okay. Hello. Time to start. Please take your seats.
Just on time.
Seconds. Piotr knows the pressure. I still have time, but people slowly sit down. He needs to start early.
To be on time. Oh. Sorry.
Trzeba się zsynchronizować. Almost. Last seconds. Okay, ladies and gentlemen, good morning. Well, maybe you know me. It happened to me to be the chairman of this conference, and I had the pleasure and some duties involved related to chairing this last session because we have to be on time. I hope everybody checked out from their rooms in the hotel because this is obligatory. This is unpleasant, duty at the last day, but I'm not seeing people running to their rooms, so I presume everything is fine. Okay, so we are coming to the end. This is the last session, and the invited talk will be given by Simon Böhme, and the subject are perovskite quantum dots as a perfect sources for quantum application. This is not exactly the title, but the floor is yours anyway. Please.
Okay, thank you very much, Piotr. I'm not sure yet myself if these are perfect, but you can build your own opinion on that. Let me start by saying I'm very impressed now even more, but this timing is even better than the Swiss clocks and Swiss trains, what I'm used to. And I'm also very impressed by the Polish semiconductor science here. I really enjoyed the whole week, and we're now at the end of it, and I really can come back and tell people that this is the place to be. And once more, thanks to Piotr and Anna for organizing this so beautifully. So, I apologize for the very long title. I just made these letters a bit smaller. It's about this one, right? Perovskite quantum dots now. And basically also this visualization pretty much sums it up where we would like to go to. So using a perovskite quantum dot or nanocrystal, I will use this term interchangeably, to produce a well-controlled stream of single photons for quantum light applications, optically or electronically triggered. So I'll give you some images, right, to make it a bit lighter, this talk at the end of the week. These are actually perovskite quantum dots. That's a few in the lab. I'm not a synthetic chemist myself, but I always like to go across the hallway and look how they make it. And actually what you could say, I mean, you see by your own eyes, these are very bright emitters. And there are lots of them. It's kind of like a coffee mug, right? That's the volume roughly that you see here. And this corresponds to roughly 10 to the 18 two-level systems that you have in there. So you could supply the world with quantum sources in this little volume. As some of you are still now arriving, I will just give you 3 questions that should follow my talk, and you can look for them. I will start with very broadly what is quantum light, because not every one of us is working on it. Some of you are experts more than me. But I will also introduce what are perovskite quantum dots. In that context, we've seen and heard some other materials already. And then finally, the question, and that's an open one, can perovskites, quantum dots, actually be good quantum light sources? So with that, I will actually now be presenting the work of a much bigger team, precisely the team of Maxim Kovalenko at ETH Zurich. These are my colleagues there. We collaborate with very good theoreticians here in France, team of Jackie Even and Claudine Cartan in Rennes. Nuri Yazdani, computational works, are also at ETH Zurich. And Dan Aron and team, they're doing fantastic spectroscopy and microscopy in Israel at Weizmann. So, okay, very broadly, to be all on the same page, what is actually quantum light? For that, we should also define what is classical light. And we have many examples here, the ceiling lights, this projector, all of that is classical light. Thermal sources, also if you go outside, the sun is classical thermal sources. So what you can do, you could think, okay, of course, it also emits photons, right? These classical sources, so quantum particles. But to get the stream of single photons, you could think, okay, I'll just dim down my source, right? Make it weaker and weaker. But what happens is then you will get a few photons, but you will not get a well-controlled stream of single photons. And that's given by nature. The photon statistics of these sources are super Poissonian, or in other words, bunched. So you dim it down, but you not always get a single photon, but sometimes one, okay, sometimes 0, sometimes 2 or 3. Tendency is bunching. Super Poissonian statistics. Well, we know we have the laser, that is our best classical, most controlled classical light source so far. Beautiful control, but in terms of photon number statistics, this is also only still random, so Poissonian statistics. Now, that is the definition then for quantum light source, and the simplest one of all would be a single photon sources. You can go to n photon sources also, but this is the simplest form, that you have really a nice stream of single photons coming out. This is what we would like to have, because then we can utilize this as photonic qubits, right? And use it for several quantum light applications. And this term you will come across, and more often this is then as opposing the classical source, this is then anti-bunched in terms of photon statistics, so super-Poissonian statistics. What to do with that? This is one, but only one out of many examples. Prominent one, you could build potentially a photonic quantum computer. With these flying qubits emitted from the source, they can be used in a, let's say, integrated optics on the chip to perform all kinds of operations. And then you could use then even classical, let's say, fiber networks to build a bigger network out of it, to build, for example, also a quantum internet. Of course, this is very flashy, a very artistic impression that is not yet there, right? But, and that is the crazy world we are living in, we don't yet have a mature technology, but there are already billion US dollar investments in this technology. So completely undeveloped, a bit provocative, but not very mature, but still $1 billion investments. You see a photo here of a construction site for a fab in Chicago by Psi Quantum. They're also building it in Australia, and the goal is to build the world's first utility-scale million qubit quantum computers. This is the bold goal, the strategy these companies here have is, and why maybe they attract some money, and this is they use also some existing platform. I liked also Moritz Brehm's comment that say, okay, know your opponents. This is kind of taking your opponent, but also using it. So this well-developed silicon platform to build on-chip a big network of quantum. So from sources to detectors, beam splitters, and so on. There's some numbers that actually give some credibility. It's going in the right direction in terms of how well you can control this single qubit states. And it's not the only company, just to mention, there's another one also on the stock market already. So this crazy amount of funding that is going in there, trying to build this. If you're more an engineer, you might like this better than the artistic impression. That is how it may look like. You have maybe a source chip where you generate the photons, and if some filter switches nonlinear units, then they're routed to a processing chip where you can perform your operations. Okay, but what we really need is, the start of all, we need good single photon sources to do this. And just for completeness, the photonic quantum computing is only one of the goals here. If you have a good single photon source, you can equally also have some impact in other areas, for example, quantum enhanced light microscopy. So here you see this better spatial resolution that has been achieved simply by using the photon statistics. So correlation of single photon counting, or you could build some ground to satellite or satellite to satellite quantum communication networks if you have a good single photon source. Also in Europe, there are some interesting developments. There's a startup company in Paris that is making good progress, using actually specifically epitextual quantum dots embedded in a high quality microcavity to produce photons and build quantum computers. Okay, so this was to set a bit the stage for perovskite quantum dots, just to know what are the competing technologies, and to start thinking if such a platform, and that's a colloidal platform, so meaning it is here floating in solution processable, if such a nanocrystal quantum dot of perovskites could be interesting in this quantum light area. And that is an open question, and I also invite you to be critical. I also like previously some provocative comments like, okay, what is this good for? we should ask ourselves, right, to go further, and where are potential pitfalls. So I'm looking forward to your questions. So I believe you've heard already perovskites, but very briefly, this is a sort of a crystal structure, in that case specifically metal halide octahedras that are corner connected, forming a 3D network where the electrons can live and eventually emit. To stabilize the structure, we have a large cation that fills this void and keeps it stable. In this case, can be cesium, but it can also be some organic cations like formamidinium, methylammonium, or aziridinium. Okay, this is the material, but I invite you now to that video, a live video of the synthesis, and then you may see some differences, for example, to MBE growth and so on. When I go into the chemistry lab, I always think it's a bit of a magic. Basically, the equation is you have some colorless liquid that is here. You pour in another colorless liquid and you get some bright emission. I'll show you that. So if it works, yeah. So the first colorless liquid is what you see in here is some lead bromide solution, so part of the elements. What we still need is the third element, cesium, also dissolved in solution, which is injected at hexane, in hexane at room temperature. Okay, you will see now from here the injection, and this real time. That's how it happens. So fraction of a second and bright emission immediately. So very simple. This is ambient, is room temperature, no vacuum. This is how they are made. So some of you actually, I think, also making those. That's fairly simple. Okay, the question is, what is the quality of now this single photon emitters? Okay, but to start first, I will list a few of the advantages that we may have. So it's a very scalable material platform, right? Solution processable, big amount of two-level system. It can be integrated easily into existing industrial platforms, solution processing on a chip. Here you see an interesting latest development. You can also, we're doing that in our group, print individual quantum dots on a nanophotonic structure. This is an example of a waveguide to build integrated photonic networks for quantum light. It's printing, right? You need some solvent and ink engineering. This can be done by engineering the tail to increase solubility and a wide variety of solvents from non-polar to polar. You see here, these are individual dots, are individual quantum dots. They're all roughly the same size and shape. So nature somehow provides us a good homogeneity. And here's the PL spectra at room temperature. They can be very well tuned across the visible spectrum. Another interesting aspect is that unlike traditional semiconductors like silicon or gallium arsenide, we don't have to care so much about the structural defects. So in traditional semiconductors, for example, gallium arsenide, if you break a bond, let's say that happens at the vacancy, at the surface interface, you will have dangling bonds, and that always then appear in your band gap, leading to non-radiative recombination and quenching. In perovskites, there's something like a defect-tolerant structure. What is meant with that? So you have here a bonding between lead and halide, and the specific type of bonding means that if you break a bond, the broken bond only ends up in a very shallow, close to the band edge, or even for the valence band inside the band. So even if you break bonds and you make faults in your structure, it doesn't necessarily introduce an electronic defect. Nature gave that to us. That is also the reason why after the synthesis you see immediately bright emission, right, without any particular passivation. But to be complete, there are also some potential disadvantages. So you see at room temperature we can make them, but also that gives you a hint that it's maybe easy to break the structure, right? They're not as rigid and stable as nitrides. It's just a combined scale that I put here between stability and unstable. You may quantify that better in terms of looking at lattice energies, formation enthalpies, the elastic constants. I think the last talk actually of this session is about super hard boron-based materials. This is the opposite. This is very soft material. And in a way, you see that these perovskites, they are closer to organics than, for example, the beautiful gallium nitrides that we see at this conference. That on a long term, so stability concerns potentially, but also there's a high dynamic structural disorder in the system. So if you give your perovskite to your crystallographer, he will, for example, come back for methylammonium lead iodide, the prototypical one, and tells you, okay, this is a cubic structure. This is correct, but only on the time scale that the crystallographer is looking at, so second time scale, right? If you would be able to follow this on a picosecond time scale, you will see that there's a lot of movement, like phonons that are activated in the system. So instead of a perfect cube, you have alternating octahedral tilts in the system. And the color code here is kind of following the deviation from a perfectly aligned octahedral neighbor that kind of they fluctuate like this. And on the right here is a nice molecular dynamic simulation. Each side here is one octahedra. And in steps of 50 femtosecond, now I'll play the movie if it works. Yes, you see the deviations from 180 degrees and they're very dynamic, moving around the structure. So a very fluffy, soft material on an ultra-fast timescale that may be relevant for photon emission. If you don't believe computation, you could also do your experiment, your Raman spectroscopy at cryogenic temperature. Everything is well defined. Nice phonon modes, rigid structure. But if you go to room temperature, you see, okay, nothing is well defined. This is a blob of many different phonons, very broad individually. It means a lot of scattering and coupling, a very, very messy structurally, very complex material. So the question is this actually a good material platform to start building a quantum light where you want to produce and process these fragile quantum states? Okay, let's check. And to answer this, we should first of all define what is actually an ideal single photon source. And I'll borrow this from Quandela company. They depicted here as their quantum candle, so the single photon source that they want to trigger to on-demand produce single photons. And that means we want to suppress these 2 photon or higher photon events, right? Single photon purity is what we want. Also, we don't only want to suppress multiphotons, but also zero photon events. We want to be bright and on demand, high brightness. And ideally, these should all be indistinguishable, these subsequent photons here in terms of color, but in all kinds of states, in polarization, in timing, in spatial mode, and so on. My proposal now is we can work towards this goal by understanding, assessing, and hopefully to some extent controlling strong coupling of the exciton to the phonons in the system. How to assess this? Well, if you have a cryostat, you can place your quantum dot in there and measure your PL spectra that's coming out. And you see that from 4 Kelvin, nicely sharp, but if you increase towards room temperature, the line width massively increases from something like 1 MeV towards some more 100 MeV. So clearly, exciton-phonon coupling is a thermally activated process, right? The electronic disorder. And if you're now at 4 Kelvin, you will see next to the single exciton line, zero phonon line, also a progression of redshifted bands, the phonon replicas, telling you there's not only a single phonon involved, but several of them. So broadly speaking, dominant ones are around 3, 6, and 19 MeV. All of these couple to the exciton. And going here, so this is the exciton energy. This is our larger dots. These are smaller dots. You see that this intensity ratio of replica to zero phonon line increases. So this coupling strength increases for smaller dots. I said there are many degrees of freedom. If you do computational studies, we find in the phonon density of states there are many, but broadly classifiable as some octahedral tilting, some lead displacement within the octahedra, and octahedral stretching modes. And the computation, and this is a single particle, single quantum dot experiment that roughly matches, as you can see. Now, interestingly, if for traditional quantum dots, also if you have an ensemble that I showed you in this reaction vessel, right, you have a broader PL spectrum, and typically this is caused by inhomogeneity. There are smaller dots, bigger dots, there are all kinds of variations. But what we find in perovskites unusually is that even a single quantum dot already is almost as broad as the ensemble. In other words, the ensemble is not given by inhomogeneity. It is given by an inside a single particle process, so a strong exciton-phonon coupling that broadens the line even of an individual quantum dots. And I'm speaking here about the room temperature situation, right? Again, if you go to larger exciton energies or smaller dots, this broadening increases. I switch now always back again here also to the computational studies. Computational studies can be nice because they give you, in that case, this DFT-based molecular dynamics. We can look at a quantum dot and follow each atom in there. And what I plot here is the root mean square fluctuation, so how mobile these atoms are. And these are all of the few thousand atoms going from the core towards the surface. And what you see that, especially at the surface, these surface cesium and surface bromine atoms here, they're very mobile. So perovskites are soft, but if you make a quantum dot, the surface of a quantum dot is even softer. So it's a structurally very dynamic material. I hope you can see that also from the back. This is the movie of the molecular dynamic simulations, all the atoms that are jiggling and wiggling on the time scale that is displayed here. Structural dynamics, but what is now most interesting is how does that translate into optical dynamics, electronic disorder. And you see that calculated on the left. So for each snapshot in time, we can calculate the band gap. We evolve it, calculate the band gap again with DFT. So what do we see? So I grew up solid state physics. We have conduction and valence band, right? These are very defined lines, delta functions. But what you see here is something like this. Right? This is the movie that is telling you, and if you take a histogram of this, you see that the band gap has a certain broadening and roughly 100 MeV. So very smeared out. And if you compare this now to our single particle spectroscopy, this is exactly what we see in the experiment. So going back, we can understand this broadening by understanding that there's a lot of structural dynamics that affect the band gap and the emission energy. I did this simulation myself, but then as a follow-up, there was a brilliant PhD student recently graduated who took that a step further, and I'd like to present that here. So he calculated that, same method again, and since this is DFT-based, you have access to the wave function. So you can plot it here. This is the HOMO wave function in this nanocrystal. And on the right here, this is just a simple cut through the 3D. So in the Y plane, XZ, and YZ plane. What you see is kind of the backbone of the structure below. But it extends kind of an S-type wave function across the whole nanocrystal. And what happens now if you increase temperature? This wave function is also not static. It is moved around by the phonons in the system. And I hope you also see that there are some red spots, and this means that electron density starts to localize on not fully on a single atom, but it starts to become a bit more crumbled. Okay, so knowing that, Leon asked, okay, how can we suppress or potentially also utilize such a strong coupling? And then he said, okay, let's just go to the more extreme structural dynamics. And he went from cesium lead bromide to formamidinium. So it's more degrees of freedom. And what you see then at room temperature, indeed, the wave function becomes even more localized. So quantified here at room temperature. So you should think of something like that. It's not like this typical like S-type wave function, but as the potential energy becomes a bit more complex, wave function starts to localize, and you may see that as a form of transient Anderson localization. How does that relate to the quantum light that we want to have? Well, it turns out it helps you. And now I have to briefly explain for all of you who may not do that on an everyday basis. And apologies for those who do, just a minute. So you can build what is called a Henry, Brown and Twist setup. You have under your microscope your single quantum dot. And now you should prove that there really is a single quantum dot only and only single photons coming out. What you do, you just introduce a 50-50 beam splitter and two detectors. So the photons that are impinging here have a 50% chance to go to detector 1 and 50% chance to go to detector 2. Now you just need some fast timing electronics to check when do these detectors fire. And at time 0 here, that means a simultaneous detection event. So no time difference between both detectors. And if there's really a single photon, you say that, yeah, it cannot be that detector 1 and 2 are firing at the same time, right? So this should ideally be 0. And you see that indeed for cesium lead bromide is not so bad. It qualifies as single photon emitter, but it clearly improves if you go to this more dynamic formamidinium. And the explanation is that you always have a probability of absorbing 2 photon making 2 excitons. But in the formamidinium systems, once they are made, they're efficiently quenched. And that's because the wave function is small, so there's a stronger Coulomb interaction and faster non-radiative Auger decay. Why is that important? Why is that useful? So typically, if you have atomic emitters or quantum dots, the recipe was make your quantum dot small, because then you suppress by excitons, by non-radiative decay. So you need to have the strongly confined system. But with this new material now, you can make your quantum dot much larger, up to 10 nanometer, still having good single photon purity. So this number means 96% single photon purity. That means bigger quantum dots, higher stability, and higher excitation efficiency, because you absorb simply much more. So these are extremely bright emitters also. Okay, and now for the remaining last minutes, I just also want to be complete and say sometimes exciton-phonon coupling can be your friend. unexpectedly maybe. But sometimes you want to suppress that. For example, if you want to hunt for high brightness. And what do you mean with brightness? Once more, just a simple illustration. You always emit with photons with the speed of light, right? So they're always fast. But a more dim single photon source would mean that you have to wait a longer time before you can re-excite the system, right? If you have a slow radiative decay, you will not get many photons out. If you have a very fast radiative decay, that means you can re-excite it much more frequently and eventually get even gigahertz emission rate, so high brightness. This is where we want to go to. And yeah, when here the cartoon, it tells you that I think we achieved that. So the trick, and we are using now a phenomenon that's called single photon superradiance. That works only if you're at a low temperature where you freeze out phonons. If you make your quantum dots larger and larger, the exciton gathers oscillator strength by becoming larger, and different excitations coherently couple, and that should give you a faster emission rate. And that is the single particle experiment that tells us, yes, that actually happens. A 7 nanometer quantum dot emits sub-nanosecond, not so bad. But if you make it larger and larger, your radiative decay rapidly accelerates. We now also be below 100 picosecond, and unless we missed something, this may also be a world record in radiative rates. I should mention outside a cavity. The typical way is you place your emitter inside a cavity, and of course you massively enhance radiative decay rates, but this is outside the cavity. You can still place it in a cavity and even make it faster. But this is just making use of the peculiar properties of the material that give you giant oscillator strength. Our theoreticians placed it down in the supporting information of this paper, several pages of nice theory, but just this is roughly summarizing it. This superradiant state can be just viewed as a superposition of your various ways to make an excitation in the system. And such a superposition state gives you a giant dipole. This is also what has been hunted for in other materials, but perovskite quantum dots actually show that this happens. Textbook physics, which should manifest in many semiconductors, now manifested here in these perovskites at low temperature once we have frozen out phonons. Okay, last 10 minutes. Simple two-level system. I've told you single photon superradiant, so high oscillator strength. You may ask, if it's a high oscillator strength, can we also see that in absorption, right? It's just the time reversal, the upward error. Well, it's just a bit technically more challenging to do a single particle absorption measurements. But if this effect is really at play, we actually should see that also in an ensemble. In that case, a thin film of perovskites on a substrate. To introduce, so at 300 Kelvin is where we don't expect any such correlation. You see the absorption spectrum here, very featureless and boring. But once you cool down, you see it already, right? Something remarkable is happening. At the band gap, at this transition, the absorption strength is massively enhanced. And as I show you, I mean, for this effect to take place, we need the coherent coupling and electronic relations over many, many unit cells. If this effect is at play, we should see an enhancement if you go to larger sizes, as in the emission before, right? And very simple to do. These experiments here in the circles are the experimental data points, quantifying this 1s, or the band gap absorption strength, increasing massively if we increase from 3 nanometer dots to 30 nanometer dots. The gray is a calculation by our theory collaborators that calculate this oscillator strength without any correlation. And in the green line, this is not a fit. It's just an independent calculation if they switch on electronic correlation in the system. As you see, it matches quite nicely. So what our collaborators tell us that the effect happens because we have electronic correlations across the entire nanocrystal at such low temperatures. Good, this just summarizes basically indeed the answer. Yes, time reversal happens in a way, and in the black squares here is the single particle radiative rates, the green experimental absorption strength, and in the circles as the calculation with electronic correlation, and here open circles without. So if you have electronic correlation, you see the same trend. Again, to be complete, and I want to stress that because temperature is important, phonons are important. At room temperature, we know it's very messy. At low temperature, we have this textbook physics that was hunted for in other semiconductors but not found. Perovskites can behave very nicely, but indeed you need this low temperature. If you only heat up mildly, you lose your fast radiative decay, and also in absorption, you lose your oscillator strength. So I have viewed it by now as two different semiconductors, at low temperature and at high. Depends where you work on. Again, a few calculations. This is the dephasing function. At low temperature and at elevated temperature, dephasing is much faster at temperatures where we have phonons in the system. And I try to be quick to have some time for questions, but I just want to mention also for completeness, towards indistinguishability, we are not yet very far, but also there you should suppress external phonon coupling, so cool down. And this is, we by now have experiments from our own lab, but I show you here from the lab of Munji Bawendi, the Nobel Prize winner, that for the first time for a colloidal quantum dot platform showed with perovskites that you can reach indistinguishability because what you want to do is you want to increase your decoherence time to approach the radiative lifetime, because then you have indistinguishable photons. Radiative lifetime is short, right? It's not so. It's not such a hard job in perovskites. You don't have to be very long coherent, but you do have to cool down to reach that. And with that, Chikuya to all of you for your attention. I'm looking forward to your question, whether that's on the high temperature studies or low temperature. Yeah, looking forward to discussion. Thank you.
Thank you very much for this exciting talk and very on time. So we have really time for questions, please.
Maybe I ask a very basic question. What is the difference between superradiance and just the localization and delocalization of central mass motion of exciton, which leads to the suppression of overlap with radiative cone and so on?
It is related, yes. So the center of mass motion, the coherence, extends over, in our case, more than the Bohr diameter, and this gathers oscillator strength that leads to the superradiance. So there's actually a terminology, if I just may, quite some confusion between what we term single photon superradiance. Based on the previous paper, we follow this nomenclature, and superfluorescence, which happens between individual emitters. So superfluorescence, we term the collective effect between neighboring quantum dots that are, for example, initially incoherently excited, and after some time they phase lock and emit a photon burst. So there's a delayed time, a built-up time. This one here, what I term now single photon superradiance, is a quasi-instantaneous effect, at least on the, let's say, 1 picosecond time scale, that is based on electronic correlations inside a single quantum dot.
Is it just a new name of this delocalization? And
it is. You can also just name it giant oscillator strength.
Okay.
That's yes. Yes.
Okay. Yes, please.
My intuition from cat selenide colloidal dots is that their surface is important because of the dangling bonds which serve as charge traps, and that leads to blinking. Do you see anything like that in these dots?
Yes, very good question. Thank you. Let's check if I have some slides. So surfaces are important. I made initially the point that perovskites are very permissive and tolerant, defect tolerance, but there's a limit to defect tolerance. So you may still get actually close to 100% pure quantum yield, but also if you look at the single particle picture, you do see blinking. By now we have nearly blinking free emission going towards squeezed states of light. But this only happens after you have controlled your surfaces. So indeed, if you have surface charges, missing ligands, they introduce these blinking events. Let me quickly check. I'm not sure if I have this slide, but okay, this is from the 2024 paper. By now it's a little bit improved still. This is, first of all, like you can emit over an hour or so. This is the on state, on ratio defined as here versus in the time in the dark state, and it's 95%. Really going to squeeze state of light, you need to still improve that a bit. But this paper was actually a synthesis paper looking at new ligands. So a long answer, but in short, is surfaces remain important, yes.
Thank you. Yes, please.
Thanks for the very clear talk. We know how to make these anti-bunch photons, but how do you make anti-bunch emitters spatially? I think it was around slide 13, so that there is a single one per side.
13, let's check. Okay, like the placement, you mean?
Yeah.
That is challenging. We're not yet there. So as you see here, this is from a recent paper using cat selenide. We are now doing that. It's not yet published, but also with perovskites. You basically indeed just have to dilute your particles that on average you would have in a single ejection event a single quantum dot coming out, and then you may fill up and make your arrays of single quantum dots. But yeah, your point is about the anti-bunch placement. We haven't achieved that. So far it is just following Poissonian distribution. Sometimes you have 0 quantum dots, sometimes 1, sometimes 2. In a one-shot procedure. You may think, okay, dilute it further, go towards mainly emitting 0, right? Then you have at most 1, and then do an iterative procedure. You check if the site is occupied. If not, you print again. This one strategy is not a very intelligent strategy, but would be one way to go to deterministic placement of one and only one quantum dot.
And if I may ask another one? So about this indistinguishability, you showed that the line width is around 1 millieV, which I guess is corresponds to a lifetime which is much faster than what you see. So
yes.
You have a lot of inhomogeneous broadening, I guess, right? So how, and also the pure dephasing was extremely fast. So how do you overcome that, and how did they get to this indistinguishable emission in the end? If you
okay.
More comments.
Yeah, thanks for the expert question. So the dephasing, actually, this was computations. There was not an expert. And that's actually 2-3 orders of magnitude off. So the computation was not yet exact.
It's the pure dephasing.
The pure dephasing, yeah. So what the group of Bavendi in collaboration with us has shown that you can reach 50 to 80 picosecond coherence time, which is closely approaching like the 100 picosecond radiative lifetime that we have, right? But you're right, so if you translate that into a line width, that should be more narrow. I mentioned just 1 MeV, but it is a bit smaller. But what we still have and need to fight is spectral jitter, so spectral diffusion due to charging events, that you have a quantum dot on a substrate, It also acts as a sensor of its environment. But if there's an environment, some charge, it affects the emission energy, and that also leads to, in a time and integrated spectrum, as I've shown you, that leads to additional broadening beyond lifetime broadening, which is important to solve. Yes, yeah.
Yeah, there is a question here.
Thank you very much for the great talk. I wanted to ask maybe a naive question. I was really amazed by how squishy this material is. And I wondered if is it possible to achieve some interesting tuning of the properties if you applied pressure to them, because they shouldn't degrade easily if they are so squishy.
So I guess we should collaborate, right?
Yeah.
With the High Pressure Institute. This is, I'm not fully expert on that, but people have been applying pressure to perovskites, and you may not even need high pressure. So gentle pressure may be an interesting.
I can imagine if they react so easily.
Yes. So if you have a higher pressure, you introduce phase transitions into new phases, because the lattice energies and all elastic constants are very low. But yes, so I think the origin of a lot of the problems we are fighting, the spectral instability, blinking that was mentioned at the surface, is because the surfaces are extremely soft. So if you find ways to rigidify surfaces, for example, maybe via some, I'm curious, yeah. Then we should be able to stabilize the structure a bit. I would think of maybe some chemistry approaches that introduce some rigidity from the surface, but very much open question. Thank you. Yeah.
Thank you very much.
Yeah. Maybe I could ask one question, because this is for me, this is a bit exotic system in which, non-radiative recombination practically doesn't exist. Does it mean that you have always like 100% internal quantum efficiency in that case?
In principle, yes. I mean, you saw the bright emission immediately emerging from the reaction without doing much, right? It's intrinsically defect tolerant. I did mention, there's limits to that. Still, chemistry needs to do something to passivate with a sufficient amount of surface ligands, so to passivate some dangling bonds. And by now we achieve 100% photoluminescence quantum yield. But you do need to work a bit on the surface chemistry to achieve that. So it's quite permissive, but with limits.
To the limits.
To the limits, yeah.
Okay. Thank you so much for this presentation. Thank you again. And it's time for the second presentation of this morning. And the presentation will be given by Paweł Mrowiński from Wrocław University of Technology. And the presentation will be on location of quantum dots position. So floor is yours, please.
Thank you very much. Good morning, everyone. First of all, thanks for organizers for letting me be here. It's a big pleasure to disseminate my results with you today, and the talk will be about the telecom quantum dots, which we believe we can isolate spatially, precisely localize their position. So probably, long story short, we probably are here, and we want to be, of course, there to localize the quantum dots and perform some photonic structures around the dot to the best extent we can. So the outline might be already clear to you, thanks to previous speaker also, who introduced us to what is going on in the world, that the photonic integrated circuits actually can do some quantum optic experiments, or quantum computation is really not a science fiction right now. It could be done, and there is a lot of effort to transfer such proof of concept experiments, which uses free space optical links to the on-chip case with using photonic integrated circuits and quantum devices, quantum sources, light sources inside, and superconducting detectors. On-chip solution also is really nice to operate at cryogenic temperatures with cryocoolers, which are available where both the sources and the detectors have its maximum performance. In our case, so basically we need to transfer to photonic integrated circuits. We need some quantum sources, light sources. Yeah. Thank you. Detectors, of course, waveguides, which provides a link, optical link between them, and processing quantum information also could be there with splitters, couplers, phase shifters. Our research interest focuses on a single semiconductor quantum dots, which should provide on-demand single photons, which also polarization entangled photon pairs could be available with some specific case, and so on. But if you think of a quantum dot as a two-level system like this, it's not always in reality the case. Excitonic picture is much more complicated. There are some inside some other recombination channels which ends up with a zoo of optical transitions. So we need to figure out how the optical transitions behave and which one we can use for our purpose. The target is also to reduce or to increase the recombination rate with photonic structures, and also it would be nice if the quantum emitter would fit to one of the telecom bands, because photonic circuits could also be extended with some fiber optic structures, or also recently quantum communication is also available in the free space. There is a shortwave infrared range in which if you can work in this range, actually we can couple photonic integrated circuits with free space links and so on. But semiconductor quantum dots is a crystal sublattice in another crystal structure. So there are a lot of details we need to understand. We try to control with different strategies. But in principle, all those features which we can learn of can be an obstacle, but could be also an advantage when you want to use it as I mentioned as a sources of photons, photon pairs, or indistinguishable photons to do some experiments with two-photon interference. This talk is devoted to the study of the quantum dots by means of photoluminescence imaging. So instead of using some reflected pattern of your sample, we can filter out excitation and map photoluminescence on the two-dimensional detector. So in the first approximation, you do this only with monochromatic camera, but if you work in a visible range, you can use 3 bands, and there is a hype now to extend this to some multispectral mapping or even hyperspectral mapping, which allows you to find the intensity, but also full spectral response of the localized bright spot. And also a lot of features can be said. You can extract from your data if you have hyperspectral response. It's a very nice example. This is a very nice example for fluorescent molecules. Simple setup upgrade allows you to resolve spectrally the single spot to a spectral distribution. It's of course not very new approach. From my side, I can show you this very quickly refer. I can quickly refer you to this many efforts which has been made for the gallium arsenide-based structures. For me personally, the most important setup upgrade which you need to do if you want to have diffraction limited spots is to insert your high numerical aperture or microscope objective inside the cryostat, where you have sample directly beneath, no optical window in between. This makes the setup really efficient to localize the quantum dots. And for the telecom bands, for the shortwave infrared range, actually we tested a few years ago very nice sample prepared by Paweł Choleva in Technical University of Denmark, who created low density, who fabricated low density quantum dots in such arrangement that you have flip chip sample with a metallic mirror below. And in this case, we learned how to do this PL imaging for the first time in our group. The resolution and the precision was not too good, I would say, but this is the main reason that our objective was out of the cryostat. There is optical window in between, and the resolution was not too good, let's say, but it was still possible to deterministically integrate photonic system and check its performance. Later on, we tried also our best with focused ion beam technique to process different design of our markers for marker-based PL imaging like this, and still the technique was checked that it worked nicely. But the precision was not there, maybe satisfactory to couple the quantum dot into very fine photonic cavities, let's say. So we need to extend our tries, and this is one example of our conceptual tries on hyperspectral imaging to get the information about the localization of the quantum dots, but also spectral response. For this purpose, we build a setup in a way that we have a line-by-line scan of our sample. When we have two SNSPD channels, one selects the full bandpass intensity count rate, but the second one can be used to record the spectral response at the given position. So you can do this point by point. Of course, if the grid would be very high resolution and you need to do large area, this will take hours. But for the case of low density quantum dots, you can optimize it a bit to make the threshold value and the intensity of the broadband SNSPD tells you that there is more than, let's say, 1 kilocount per second, you start the spectral analysis. And in this way, you collect really hyperspectral image. But this is the trade-off. Like this, it then requires a very complex post-processing. Because this is a long-term experiment, you need some pattern matching procedure to make the grid regular again. And with some interpolation and nonlinear fitting, you find a dot, you have the spectral response, but the accuracy is not perfect, let's say. So we decided also to try the multispectral approach, which is also some kind of a trade-off. We know that that sample from Technical University of Denmark emits around 1.7, even 1.8 micrometers, so 1.55 emission is a tail of this. So if you apply some long pass filtering, our camera efficiency is limited to 1.7 more or less. Typical picture is that you have multiple quantum dots next to each other, so in a close proximity. If you apply then more narrow band passes, there is a limit of your sensitivity for your camera, and then you limit noise, but the intensity of the dot is also so rather low and doesn't give you enough precision. So we found also a trade-off when we use 40 nanometer band pass and then actually we can find with some features here, if we find those features like the isolated quantum dot, the spot then looks very symmetric. There is low background noise around. Peak intensity comes only from the single optical transition. Then the fitting accuracy of just Gaussian fit is there is a high correlation with the Gaussian, two-dimensional Gaussian function, and the fitting accuracy is really nice. Also, yeah, you can try to perform using this multiple filtering some false color scale imaging, which also is actually practically very important because sometimes the spots are gray. So there are no single optical lines in a spot, just a constant background which arises, and in this especially you think this is a quantum dot, but this is some background, no emission lines. So if you tend to distinguish quickly between quantum dot lines and the background, you need to do some such a color images, multicolor images. And actually, just half minute, yeah. For our on-site technology, we recently also achieved some quantum dots of low density. We were able to tune it to the close to 1.6 micrometers. And we analyze also those samples with a large area case for using the less magnification. And yeah, we constructed also it was a successful demonstration recently to fabricate DBRs below the low quantum dot density, which fits nice to the simulated dipole emission enhanced by the DBR. So we have ensemble emission and very bright emission lines at the range we want to have. And with this new approach, we found really nice examples of quantum emitters, two types of quantum dots. We know kind of very well the spectral pattern, and also those, together with this PL imaging, we can use a planar sample, select the quantum dots, stay there for a long time, check many excitation schemes, and do such a nice results, confirming single photon emission purity. And also we can perform two-photon interference experiment, which demonstrate without post-selection, without subtracting noise, without any advanced fitting procedures with deconvolution and so on, just the raw data with 5 nanosecond window. Without the post-selection, the visibility of the interference is quite high. Yeah, basically this is what we want to do in next future. We need to bring that actually set up to earn to the best of what we can do, bringing microscope objective into the cryostat, have some piezo stacks to control the sample position, and this is our, let's say, last week results we can process to make some further nice results. And with this, thank you for your attention. Thanks for the people who were involved in this investigations and findings. Thank you very much.
Thank you. We have a time for one question. Yes, please.
The line width of best quantum dots can obtain?
So it's around 1 nanometer, which is 40 micro EV. Okay. 40 micro EV, more or less.
Okay, we have to proceed. So thanks again for your presentation. And this is the time for presentation of Jacek Kasprzak from CNRS Grenoble, and the presentation will be on tungsten selenide studies by 4-wave mixing.
Yeah. This is not the first slide. Słucham? I don't know. Well, anyway, welcome everyone. I will be on time because I think we are getting hurry and I see that our chairman is very strict. So it's my big pleasure to be back again here at the Jaszowirc School. It's not my first time. It's not my last time, definitely, but as far as I remember, it's my first contributor talk that maybe I will give with no slides. So I would like to thank the program committee for giving this oral slot for the work which is not published. And I will here standing you on behalf of Jinwoo Jung, who is the first author of this talk. And I would probably need some slides. Yeah. So this is how I want to start. As you see, I changed my title a little bit. I have a bit more experience than Jinwoo Jung, and what I want to tell you today is how cleaning two-dimensional materials allows us to access to the new physics of these structures. I will say a few words about the people who are involved. So the first author is Jinwoo Jung, who is a postdoc with me in Grenoble in 2025. Now he's back in Korea, and this is the reason why he cannot travel so often back and forth between Europe and Asia. But he will be back at Institut Nel in Grenoble in about 1 month. So Jung-Won Kim is probably somewhere here in the audience, very shy guy here on the back, doing a lot of work with me in Grenoble, but mainly involved in the project that we are pursuing in collaboration with University of Tsukuba in Japan. So this is not what I'm going to talk about today. And Sung-Young Lee is a more senior postdoc, which is very much involved in fabrications of these structures. So all these three Korean gentlemen were sent to Grenoble via long-standing collaboration with Kwan-Suk Kim, who is at Busan National University. Julien Renard and Gilles Nogues are the local researchers. Tomek Smoleński, I think everybody knows here who the guy is, currently in Basel. And actually, this talk starts from the meeting that we had here 4 years ago when I was giving a tutorial talk. Tomek was here telling you about the discovery of the Wigner crystal. Then I started to collaborate with the group of Atachi Mamoglu in Zurich, and I had this scientific catharsis, and I understood that it's very important to have clean two-dimensional materials. And this brought us to this Opus project, which I'm currently pursuing with Piotr Kosacki at the University of Warsaw. Okay, so this is a short outline. I will tell you what is clean and how to assess it, and I will demonstrate you this clean gated WSE2 device that we now fabricate in Grenoble. And with this WSE2 structure, I will point to you signatures of the Wigner crystallization that we are directly accessed by using coherent spectroscopy, and I will finish by giving some current plans. So with two-dimensional materials, we essentially are rediscovering the physics of quantum wells. So essentially, if we have a carrier in the semiconductor between two semiconductors which have a higher band gap, if this distance is comparable with the Broglie wavelength, the particle starts to be two-dimensional. So this brings us to the nanotechnology, because we have essentially, this is around 10 nanometers, we are starting to have this two-dimensional motion of a carrier inside the gallium arsenide. So if this electron meets a hole, they will start to correlate, create an exciton, which is a very fragile bosonic particle of around binding energy of 5 millivolts. So with two-dimensional materials, with transitional metal dechalcogenides, we are rediscovering this physics. At monolayer limits, they have a direct band gap, they have the valley structure, so they have the hexagonal structure, so K and K, two inequivalent valleys last in graphene. but with the band gap in the near infrared range, right? And this is what we are using in optical spectroscopy. The big difference with respect to the standard semiconductor is increased effective mass. In gallium arsenide, we have 0.06, something like this for electron, and here effective mass is much larger, and also reduced screening, right? So if we have a just pair monolayer, the epsilon is 7, and it is twice more in let's say, gallium arsenide. So this gives us robust exciton, enhanced correlation energy, in this very rich spin valley texture, specific selection rules linked with the helicity of the light, but this will be not very much important in this talk. So, of course, there's been a huge progress in making the epitaxial growth of these materials, specifically in group of Wojtek. But you see, if we are working with optics, so this is a typical diffraction limited spot that we are using, and we still are faced with a world which is mixing B layers, zero layers, and we are still very much prone to disorder in the system. We can exfoliate it, and maybe we'll have monolayer, and we can now start to functionalize this these objects, right? So we have WSE2 monolayer inside the HBN. HBN is used as an encapsulation material with a very high breakdown voltage, which is very useful in order when we like to make this kind of capacitor structures. So these two gentlemen had a huge impact in this field. The last time I checked, they have 300,000 citations and H factor of something 270. We can contact this using full-layer graphene. And maybe this will be replaced in some future with our local experts in HBN. We can contact this, and we can inject electron and hole at will. And this is what you want to do. But life is much more difficult, so we have disorder inside. So when we encapsulate, we have lots of cracks, wrinkles, and bubbles. We have induced strain by stamping. We have unintentional doping from the substrate. So usually we don't have two-dimensional materials, but essentially the electrons are localized by disorder. And so we've made this huge effort in order to get rid of this disorder. And when we have clean sample, the optical response is directly linked to the dephasing time, and we have free excitons which can diffuse, as probably has been shown at the beginning of the school by Alexei Chernikov. And in the dirty sample, everything is localized, and we are dominated by inhomogeneous broadening. So over the last 30 years, we have been using coherent nonlinear spectroscopy in order to access to this, to assess the disorder in the structure. Of course, I don't have the time to tell you all the details. It's a reflectivity experiment in which femtosecond pulses are modulated in a way that in the detection we can get rid of the resonant lazy light, essentially. And this is what is called heterodyne detection. We combine it with spectral interferometry to gain in the sensitivity, and we have quite a sensitive probe of optical properties in this material with this special construction of the full-wave mixing transient which gives us photon echo. And we wrote 80 pages tutorial about this in the recent year. And essentially, we can assess disorder by looking at the full-wave mixing interferograms here. So this is the typical spectrum on the disordered samples, and this is what's going on when the sample is clean. We have a very, very nicely defined Rydberg states, and from what I see, at the moment that we have an access to Rydberg states, the sample is essentially getting homogeneous. And we assessed it by looking at the photon echo, which I also will skip because I see that I have 3 minutes left, and I want to somehow give you the results that I want to convey in this talk. So we need to create this sample. We need to be able to inject carriers. So you see this is this clean WSE2 monolayer that we are able to fabricate. And in this case, the optical response is dominated by by Fermi polarons. So essentially this Bose impurity, which is existing in the Fermi sea of carriers. And when you increase the carrier density, you will see the two branches. One is repulsive polaron, which is blue shifting. The other one is attractive polaron or tryons, negative tryons, which are red shifting with this characteristic siglet-triplet splitting, which is very well resolved in the structure. So this is a structure from Munich, from Jonathan Finlay. This is our structure measured in 4-wave mixing spectroscopy. This is a microscopy, so we can measure, we can image our samples and pick up the place in which we can inject the carriers efficiently, and which effectively the coherent response is dominated by free induction decay, so no echo, so that we can pick up really the place where we have no disorder. This is a gate voltage characteristic, spectrally resolved. We see repulsive polaron, these two tryons, singlet triplet tryons, and the attractive polaron on the whole area, which is not split because the band, spinel bleed band is too far, 400 millielectron volts away. Okay, with 4-wave mixing spectroscopy, we of course have an access to coherence dynamics from which we can assess homogeneous line width. So we did this experiment. The details you can read in the paper, which will be submitted before the end of the month. I have 1 minute to tell you about how we can have an access to the Wigner crystallization. So when I looked up what the Wigner has been doing, he's an absolute star of modern physics. You will see this poster that he's been architect of modern physics. And this is the original paper when he says that the magnitude, he's talking about correlation energy about electrons, and that if electrons had no kinetic energy, they would settle in configuration which correspond to absolute minima, right? And they will form this characteristic crystal in a triangular shape. And here it comes back to the beginning of my talk, because we want to have a repulsion energy which is much higher than the kinetic energy, right? And in this settings, what plays the role is the active mass, which is high, and the dielectric constant, which is low. And this brings us to this RS, which for gallium, which for tungsten diselenite is like 40 at standard cryogenic temperatures and the reasonable doping densities, whereas for gallium arsenide it's essentially not accessible at this temperatures. You can maybe put magnetic fields in order to engage this Wigner crystallization, but here is just created spontaneously, and the hallmark of this Wigner crystallization is the Umklapp branch, which we could see in the reflectance, and which we also see in 4-wave mixing, that I just showing you at the very end because I'm out of time. And we also see this Wigner branch at Wigner polarons that are there. And this setup is now available at Warsaw University, and I'm sure that you are going to see many talks about this in the following years, also at this conference. Thank you very much for your attention.
So much. Okay, we have time for questions. It was that clear for everybody? Oh, yeah, Tomek.
In 2D helium, if you put on the surface, this gamma is 170 or something. If I understand, you have degenerate gas, and because of that, you have this RS 40. It comes from, who calculated this 40?
One of the person, Głazov, Misha Głazov, that has been doing this. I think in the original paper from Tomek from 2021, there is also calculation in the supplementary material. There's very long supplementary material where this calculation has been performed. Yeah.
Because it's far from trivial.
Yeah. Here, the 40 not 40, the importance is the hallmark, experimental hallmark of the umklapp branch that, that we can see or not, and only we can see it when the sample is clean. If you have any disorder, this is all this obscured straight away by localization, by inhomogeneous broadening. So what I wanted to tell you is that there is a real need to create disorder-free samples, which is very, very difficult.
Okay. Thank you.
Okay. Thank you very much again. Okay, it's time for the next presentation, and the presentation will be given by Weronika Solarska, and the title is Dynamic Control of Light, Electrically Tunable Photonic Traps, and Weronika is from Warsaw University, so please, floor is yours.
Thank you very much for an introduction. I'm Wiktoria Solarska from the Faculty of Physics, University of Warsaw.
I'm sorry.
No problem, it's a common mistake, so don't worry. Today my presentation will be about electrically tunable photonic traps and how we can gain control over the light using them. So let me start with the literature, because I'm working with structurized microcavities. So as you can expect, to this point, many macrocavities have been structurized, and these are the examples from the literature. And on the right, you can see one of the examples when they introduced change in the width of the microcavity. They change it locally, and as you can see, they put those mesas, because we call them mesas, in a square lattice, and what they observed was a bend. The other way to do that is from the group of Sebastian Klempt, and he has a talk. He had a talk on Sunday, and they showed that you can have also a potential in form of micropillars, and you can have topological edge propagation, which means that this edge propagation will be there even though some defects or corners in the structure. So it's topologically protected, and I will tell you more about it later in the presentation. The other way is to locally pump structure. For example, in polariton systems, you can locally pump, create Bose-Einstein condensates, and you can make them interact. And with it, you can emulate some interesting Hamiltonians. And the nice thing about this type of potential is the fact that you have tunability, because you can change the distance between the nodes. Because in the other two, when you prepare your structures, it's done, there is not much room for tunability. And I want to show you another way to have a tunable microcavity, which I'm working on, and it's called liquid crystal microcavity. And in this structure, we are using a liquid crystal, which consists of elongated molecules with different refractive index at different directions. So you can see that for horizontal polarization, this molecule is long, so the refractive index will be high. And for the vertical polarization, it's the opposite. And the nice thing about this material is the fact that we can rotate the molecules by applying an electric field to the structure. And as you can see, the refractive index for horizontal polarization is changing, and with it we can change also the energy of this mode, and we can bring different modes into the resonance. We can bring modes with the same parity, and we do not see an interaction between them. But when those modes have different parity, there is an interaction because we have high degree of circular polarization, and we see two branches at minima at different, at k vectors that are not equal to 0. And also one of the branch has sigma plus polarization, while the other one has sigma minus. And this type of dispersion was first observed in semiconductors. There is the effect which is called Rashba effect and also a Dresselhaus effect. And in our structure, we have both of this effect and with the same strength. But of course, for semiconductors, it's not polarization, it's spins. But we can say that we have an optical analog of this effect. And with our microcavity, we can easily go to this regime just by applying a voltage. Also, in our group, structurized microcavities was also shown. You can see here the examples of microcavities with self-organizing liquid crystal systems. So you can make the liquid crystal to form potentials in form of stripes, and it's called uniform lying helix. And with that, my colleague observed formation of the band. And also another type of uniform lying helix, slightly different because the potential landscape was different, was presented by Joasia on Monday. And with it, you can see the formation of an SSH chain, and I will talk about it more later. But with those type of system, it's really not very easy to control the parameters of the potential. So for example, we cannot introduce a defect very easily to see those topological effects, but we can do it more deterministically using etching. So I'm starting in my case with glass and ITO electrode. Then by different technique, I can etch the electrode, then DBRs are deposited on top of this structure, and another substrate without additional potential is taken, and everything then is filled with liquid crystal. And I'm using different techniques to do that. So first is focus ion beam, so we can precisely etch our IATO using gallium ions. And this is what I did. So this is the AFM picture of single potentials with different sizes and different depths. Unfortunately, the focus ion beam is not working right now, so that's only what I was able to do, and hopefully I will prepare a more complex system in the future. But while waiting for the focus ion beam, I tried chemical etching. So we can use chromium mask with structures, and we can deposit photoresist on top of IATO, and by using light, we can put the structures into the photoresist and then develop and then chemically etch them. And I got really nice stripes. So you can see here the picture of them, and I got nice results. And also I will use electron beam lithography. I'm just started doing it, and I hope I will get some results, but I don't have any right now. And this is the results for chemical etching, so for the stripes. So as you can see, I saw the formation of the band. And then when I apply voltage, not everything is moving, only the horizontal polarization, in this case, is changing its energy, and I can go to this Rashba-Dresselhaus spin orbit coupling regime. But those type of structure are not as interesting as the topological ones. So in the future, I will prepare them, but to do that and to not do it blindly, I perform some simulations. So you can see that I use the Hamiltonian, not only changing the spatial potential, but I also have the terms for T and TM splitting and also the Rashba term. And as you can see, I got a really good agreement between the simulation and experiment. And with that, in the simulation, I could go a step further and introduce SSH chain. So I started with a chain where all the nodes have the same separation, and they are in form of Gaussian potentials. So with a normal chain, I observe a formation of a band. Then I can introduce an SSH chain. So I'm changing the distance between every other node. So as you can see now we have nodes that are close to each other, so the interaction is strong, and the nodes that are far from each other, so the interaction is weaker. And with that, I can see the opening of the gap. And then, when I'm introducing a topological defect, a state in the middle of this gap appears, which is a topological state. It should be in the spectrum, even though some local defects could be in the structure. And with simulation, I can also see how it looks in Rashba-Dresselhaus spin-orbit coupling regime. So as you can see, this state has a strong circular polarization, and one state also have like both of those polarization. And I hope I will see the topological state in the experiment. I cannot wait to see it. And the other technique, which is new in microcavities, is photoalignment. So in the previous case, I could locally change the width of the microcavity to have a potential, but here I'm locally changing the refractive index. And it is done using the same chromium mask as before, but now the light is passing through a polarizer. And I'm using, not me, but the people that are preparing it, are using glass, IATO, and DBR. And on top of that, there is a special polymer. And this polymer will remember the polarization of the light that was shone into it. So we can locally make this polymer to remember one specific polarization, and then the molecules will follow this polarization in a structure. So as you can see, we have like different areas, like green one when molecules followed this type of polarization, and the pink one which are perpendicular. And the top DBR has no such a structurization, so with that you can see that on the pink areas the molecules undergo a twist, and it is locally changing the refractive index, and we can have potential by using such a structure. And you can see that also we saw the formation of the bands in also a stripe pattern, and we can tune it by applying voltage. So as you can see, a lot of parabolas, a lot of things are happening. It's much more richer than a wet edge sample. And we are now developing the simulation, the theory to understand what is happening, but the picture is much more richer. And we can also look at it by making a cross-section and in angle equal to 0, and to plot it against voltage. So we see the anti-crossing between bands. So there is some interaction between horizontal and vertical bands. So it is much more interesting. And with this project, we also want to prepare topological defects, not only trivial cases. And to sum up, I showed you two techniques. One is connected with etching, and the other one is a new one in microcavities, which is a photoalignment technique. And with this project in the future, I want to not only focus on trivial cases, but also prepare much more interesting lattices and observe topological effects. So thank you very much for your attention.
Thank you. Yes, the presentation is open for questions. Yes, please, Tomek.
In electronic system, we use topology for metrology. I wonder what are kind of ideas you have in terms of quantum, let's say, sensing, quantum metrology. So.
Okay, so I will go back to the slide with simulation. Oh, this one. So with that, because this topological state is protected, so like the threshold for lasing should be lower, and also this defect should emit light, even though some local defects are in the structure. And also here we have, from this state, we have two polarization, and they will be emitted in different directions. So we have like a laser which emits light in different direction, and this light has a strong circular polarization.
Okay. Yeah.
Hi, thank you for the presentation. I have a question to the next slide.
Okay. Yeah.
So I was wondering, why do those pink molecules twist? Because there is no patterning on the top.
There is no such a patterning like that, but there is a patterning where all the molecules should follow, be in the same line. So there is a patterning, but not with additional structures.
Right.
Yeah, so they have to follow it and undergo twist.
Thank you. Do we have more questions? Yes, please.
Congrats, this is beautiful. Beautiful
Thank you
platform.
very much.
If I understood correctly, it is that you imprint the topology and the things you can do with the etching and structuring, but then you still have a homogeneous electrode, right? The ITO.
Like the top of one is homogeneous, but we can also try more patterns. So have a different structure on the top and on the middle, and twist them to have some more effects also. So it's not only the bottom bottom DBR.
So would it be possible in future to address individually, locally, the ITO from below, like a pixelated structure?
Probably, yes. Yeah, I hope so, yeah.
Okay, thank you.
Thank you.
Thank you very much. And thanks to the speaker again. Thank you. And hard to say, but we are coming to the last presentation of this conference, and this role has been given to Neville Gonzalez-Szwadzki. And as it is a hard situation, he will be talking about the hardest possible materials realized by computer.
Thank you for the introduction, and thank you for being until the end. And then I have the opportunity to present my results. So yes, I will be talking actually about two-dimensional boron and how deformations influence the properties of two-dimensional boron, but in a context of super hard materials. So I want to start by saying that I'm not talking about boron nitride. It's pure boron. It's pure boron usually forms a lot of two-dimensional structures. One of the stable one is this called alpha borophin. I picked that one because, as you will see in a moment, it's pretty much the same as the graphene in terms of structure. I will try and show you the results of deformation of both of them actually, and how this influences the electronic properties. As I mentioned to you, there are a lot of two-dimensional forms, single layer forms of borophins. Starting from the oldest one, it is called Bustani structure. It is just a triangle, borons arranged in a triangle lattice. This actually form is buckled, so to make it flat and more stable, we create vacancies or holes. And forming holes, it's just infinite in an infinite number of ways. You get an infinite number of allotropes, or two-dimensional forms, simply. The well-known or experimentally accessible are those that I'm showing here, those three. If you keep creating holes, of course, we will end up in a honeycomb-like arrangement. This honeycomb arrangement, if for a freestanding borophin, is highly unstable, so should be stabilized. Most of the structures are grown on metallic surfaces. So this is highly unstable. The most stable arrangement actually is none of those. Here is the alpha borophin. that also was is accessible experimentally, but in the form of bilayer. I would love to say that all this borophin business came when I started researching on it, but it's not actually true. In the 1950s, there are already descriptions of metal borides that contain boron layers in the form of honeycomb-like structures. The most famous probably to you and well known to you is metal diborides, because later on they were famous because of the superconducting properties that some of them have. And the also quite well-studied example is tungsten triboride that contains a honeycomb-like lattice inside, or lattices of boron atoms. The problem with tungsten triboride is that in most cases when this material is produced, it's actually very hard, it's super hard material, but when it's produced, there are some contamination, the extra boron atoms that get into the material, and if you keep contaminating, or I would say decorating the honeycomb-like structures, or inside in between the atoms here, the metallic atoms, what you will end up with is with the tungsten tetraboride, which is actually made up of alpha borophins that are stuck, that are in between the metallic layers. So the problem with boron or tungsten tetraboride is this is becoming soft. Until very recently, nobody understood why. The bulk modulus, I mean, the compression of the material still is okay. Well, here I have the numbers versus the boron content inside the metal boride. And starting from tetraboride until the triboride until the tetraboride from the side, the bulk modulus is quite okay, but the stiffness, the shear modulus, I mean the moving layer, one with respect to the other, is just lowering down dramatically. This is because nobody was studying those materials from the perspective of formation of borophins inside the metal borides. So once the borophins are there, they are stable as entities alone, and they are loosely coupled to the metal atoms simply. And the overall hardness is just lowering down from a very hard material, super hard actually, to a soft material. Okay, so, but let's go back and look a little bit. I promised you to compare those two structures. So the honeycomb-like borophin, that is very common in metal borides, with the alpha borophin, which is nowadays accessible experimentally as a double layer. If you compare them, I picked a unit cell with 8 atoms only. And here is the unit cell. If you look very carefully, those atoms that are at the edges they stay where they are. But if we rotate this hexagon by 30 degrees, we can transform the honeycomb-like structure into borophin, alpha borophin. What it means that the deformation, actually, the little bit of change of the hexagon, of course, it may take a lot of energy, but the transformation is actually very simple. What happens here is roughly the boron atoms double the number of bonds that they form. The network is just simply from 12 nearest neighbors here to 21 roughly that they have in such a configuration. If you look at the very simple time binding model that actually it's just taking into account the arrangement of atoms. It is not particularly does not contain okay, you can have any atom actually in that arrangement and we'll have the same picture. So in the case of the honeycomb like borofin, there is a well-known Dirac-like behavior. In this arrangement, we have a metallic band here, and the property of this alpha borofin is just a metal. And most allotropes of boron are metallic-like. So what happens if we try to deform it? Actually, I was looking whether the deformations, any kind of deformations may open the gap. This is what I was looking for. And I'm showing just one type of deformation here. It's just elongation along the a-axis. And what is happening, of course, is something expected, that you cannot outperform graphene. Graphene is always more stiff than any other material. But what is surprising here is that up to 20% of deformation, you still have a structure that has a deformation which is reversible. In terms of the Poisson ratio, the response to the deformation in the perpendicular direction, both structures have the same almost response. This is alpha borofin with respect to graphene. What about the electronic properties? I mean, it is even more surprising. Any deformation that you do to this alpha borofin, no matter what you do, will stay metallic. So this is zero deformation. The band structure looks like that, and the 20% of deformation actually in this direction that I was showing is also metallic. So the atoms try to rearrange in such a way to keep being metallic for the whole structure. If we compare, this is actually the message to take home, if we compare the material with other materials that also were discussed during this conference. So in terms of hardness, the alpha borofin, although it's a metallic system, it's pretty hard if you compare with some of the materials that you have here in the list. Of course, it's not outperforming boron nitride and graphene. But keep in mind that all those materials are either isolators or semiconductors with well-established bonds, with very directional bonds. And here we are talking about a metallic system with delocalized electrons. So this number is actually pretty a good number, I mean, in terms of stiffness. Okay. With that, I want to finish by saying that there is a whole topic that we are starting with the mechanical properties and how they influence the properties of borofins, two-dimensional systems, but not only in the context of two-dimensional systems alone, but also in the context of this bulk metal borides that I was showing to you. The previous topic that last year I was presenting about gas sensing and biosensing is nowadays is very advanced. A lot of work is coming. People, researchers working on this in this field, and also the fields that were from the very beginning explored, like batteries, ion storage, electrocatalysis, and hydrogen production. Those are more or less the pillars of applications of borofins right now. I wish to thank my students, two PhD students that are with me actually at this conference. Subrata is exploring the structure and properties of nanostructures, of course, boron-related nanostructures, and Sonur is experimentally oriented, but also working on some theory, especially on the electrocatalysis on borofins. Thank you for your attention. I wish to leave you with this slide. There is a workshop on boron and boron-related materials. If you have a single atom in your sample or in your theory, please join us. There is still time, and there are available spots for you to join. So thank you so much.
Thank you. So do we have hard questions to Neville? Yeah, there is one.
Okay, so thank you very much for a very nice presentation. I have a question concerning using this, let's say, this layer which is conducting as instead of graphene on top of boron nitride. Do you see some perspective of growing this?
To be honest, this is our next topic, and we want to explore this, how to grow. I'm talking about real growing on boron nitride substrate, or isolating substrate, because at the moment, nobody was succeed with that. So we want to do it at our department. So yeah, yes.
Okay.
This is what we want to do next.
Okay. Do we have more questions? And what is actually, from the material experimental point of view, the situation with these borophines? They are hard to synthesize, or
they are
easy?
not hard to synthesize. The problem with them is that they are mostly very tightly bound to the substrate on which they are grown. So, but there are also versions of borophines that come with as a bilayer systems. And as a bilayer, the layer which is on top of the one that is attached to the surface, the one that is on top is already less bound to the rest of the system. So there are like kind of hope that at some point we will be able to detach the borophines from the substrate. Yeah. So.
But this is also used as a kind of a protective layers for
No. The oxidation of the layers, the problem of oxidation would be a next like a step forward. I mean, we will have to cover it with, let's say, with boron nitride. It's a good cover, actually. So, but at the moment we have problems with detaching them from the substrate.
Okay. Do we have more questions? If not, let's thank Neville. And as well all the speakers of the conference. So thank you very much all for your participation and your contribution to the conference. And let me say a few words. Yeah. So we are after, depending, 5 or 6 days of the conference. I do hope you enjoyed this. I do. That was good time, and I think we had, I mean, trivial to say, many interesting and very good level presentation. And so let me. Let me change the slide. Well, this is the last moment when something can happen, but. Anya, maybe from your computer we can do it, no? Right. A ręcznie się przesuwa? Okay, so the catastrophe is not that big. So let me. Yeah, we have a. Okay.
Sorry for this. Sorry, I have no idea. We will just show it like that.
Okay. Okay, so let me change the slide. So some statistics about this conference. We have around 230 registered participants this year, and of whom around 30% are women. And interestingly, among PhD students, we have like 40% of women. I think this is something which is very positive. I mean, in Polish science. Of course, we are not talking only about Polish students, but the statistics are very nice. It's a bit pity that if you go towards more, let's say, adults, researchers, this percentage is going down, but not that much. We had altogether 4 school lectures, 15 invited talks, 6 highlighting talks, and 40 contributed oral presentation, as well as 130 posters. So that was relatively, I mean, as for Jaszowirc, maybe not enormous, but we had really good attendance. I'm sorry. So, you know, hoping that you enjoy the conference and the program, I would like to stress that this is, of course, the program is actually formulated by the whole program committee, or Jaszowirc committee, as it is locally here called. And I would like also to stress that we had this topical division, which we assumed organizing this conference, and we had a topical chairs, and that was Andrzej Wysmołek, Maciej Pieczarka, Magdalena Birowska, Grzegorz Sęk, and Piotr Wojnar, who really helped coordinating, you know, the program. So finding the best presentation and ordering them and so on and so forth. So thank you very much for that. Well, it's again organizing the conference is a complicated task, and somebody has to do it. And usually the chairman is not the main person to really take care and responsibility for all the duties. So I would like to acknowledge, that the main persons were Anna Kafar and Anna Reszka. Ania Kafar as a conference secretary and Ania Reszka as the head of the organizing committee. And I would like to very, very much thank Ania and Ania for their contribution and work. And this is, well, this is not kind of a... Okay. Okay. So yeah. So I would like also to say that, well, there are many conferences. I participated in the organization of many of them, and something which is quite exceptional for the Jaszowirc conference is the organizing committee. I already thanked Ania Reszka, but all these persons are so competent and efficient that the work, I mean, organizing this conference is kind of a pleasure, and it's smooth. And probably you know that all the problems which arise, they are quickly solved. So thanks to all technical team here. Thank you very much. And you know, the effort of people is the most important, but we also have pleasure and obligation to acknowledge the financial support also of Polish Academy of Sciences, of all our sponsors and exhibitors who contributed to the success of this conference. The patronage of Ministry of Science. Well, I hope this patronage will somehow solidify in the future also in constant support of semiconductor community in Poland. Because there are many big words in Poland about the strategic role of semiconductors, but I hope the facts will follow. So I take this patronage as a kind of a sign of the goodwill and maybe future interest of government in Polish semiconductors. So finally.
Sorry, I have to interrupt you. This is the old presentation. Nie mamy informacji o proceedingsach. Sorry, I have to spoil the fun. So before the fun, because we tried to solve the problem, we have an older presentation. There is no information about our proceedings. So I would just like to mention that the proceedings are ongoing. The submission is open. We will send all the information through the email so that once you are back, you can start thinking about writing the papers. We hope for very nice papers for this. There are opportunities to write both original articles, but also review papers. So this is why at least I tried to talk to some of you and others, also to the invited speakers, that if you feel that a review paper could be a good let's say, conclusions from your talk, it would be great to also receive it. And the whole initiative is done in such a way that the chairs of the topical sessions here are included as the guest editors of this special issue, so that we hope that we will, let's say, keep the quality of the papers great and also be able to encourage everyone to try to contribute to this proceedings. So I'm sorry, that's all of my notice.
That's important. We count on you in case of proceedings. I know that the proceedings are not that fancy, but I hope you will find a good subject which can be published. I mean, not destroying your plans concerning, you know, maybe the more serious publication. But I think it's worth at least trying to find a good subject for that. Finally, we had some moments of good weather. We had nice mountains around. I saw that people did a lot of hiking, biking, anything, many sports, tennis even. So I hope you had fun and you enjoyed the conference and please take only good memories of this event back home. And as the conference is coming to the end, I would like to announce that the next conference will be chaired by Piotr Wojnar, and I, saying you goodbye, I will pass the microphone to another Piotr for the new conference.
So, thank you very much. Since I have the microphone, I would like to thank you for being the chair of this conference. I think that I say it in the name of all participants. So, thank you very much. Okay, so I have the pleasure to announce you the Jaszowirc conference next year. It will be held here in the Klimczok Hotel. And yes, these are just preliminary arrangements. And the preliminary dates is the 12th of June, which will be the starting of the school. The 14th of June would be the starting of the international conference. And yes, I kindly invite you all to participate in the new event. So thank you very much and have a safe trip home.
So this will be a platform for all kind of different materials, right? I mean, you use now.
Liquid crystal?
Yeah, and
Yeah, we will try dyes to have photonic condensation. Yeah, in the future, hopefully. Yeah, so now the project is photonic dyes, but we will also work with some nanoparticles, so we are trying, but the dyes is our priority.
And that's why? Because we have to middle or still from the design?
Dobra. Dziękuję bardzo, bardzo było miło. Mam nadzieję, że zostajemy w kontakcie i będziemy na pewno unikać od albo zapraszamy
Yeah. Okay. Yeah. So
Wszystkie akumulatorki były jedne niepodobne. Z tych też są akumulatory czy baterie? Baterie mogą, ale też wyjmijmy, bo jak wyleje, to będzie... Nie, to jest nowe pointery. I dwa działają, reszta gdzieś gaśnie. Gotowy do
Coś do jedzenia? Nie. To ja też bardzo dziękuję za wszelką współpracę, pomoc i tak dalej. Ale nie wiem, jak będzie się przetrzeć,
jak pamiętam, że ja już to próbowałem. Oni za chwilę musimy poprosić wszystkich o opuszczenie tak, cały dzień.
The call for the next event.
Thank you.
It was nice. Do zobaczenia. It was nice to see you.
Relacje z fundacji tam.